Should I start? Or are you gonna introduce?
We introduce the session first,
Yes.
but we get started. Okay, Okay, hello everyone, and well, thank you for making it that early this morning. So I am Oel Kervadek. I am from the University of Amsterdam, and I will co-chair the session with.
My name is Xiaofeng Yang from University of Chicago.
Okay. So without just some rules, we have two microphones for the questions. The microphone won't travel within the room. So if you have some question, you can already start to get closer before the end of the talk. And our first talk actually is entitled Fast and Explicit Slice to Volume Reconstruction via 3D Gaussian Primitives with Analytic Point Spread Function Modeling by Mike Dannecker. So now the floor is yours. You have 10 minutes.
Nice. Thanks a lot. Yeah, thanks for being here so early. Now it's not that easy, but yeah, bear with me. This is like a talk about slice volume reconstruction, which is like a general method, and we will analyze it in the setting of fetal brain MRI. So let's first look at our problem setup. What is slice volume reconstruction? So what we have is the problem of registration and super resolution both at the same time or interleaved from 2D images into a consistent high resolution 3D image. And this is also a procedure that you do standard for fetal MRI. And the case why we have to do this is, or the reason why we have to do this is that a fetus in the mother's womb is moving during the MRI acquisition. So we have to come up with very fast acquisition sequences where we just acquire like a slice, one slice at a time. And these 2D slices can be acquired like in under a second. So any fetal image, any fetal motion is kind of like frozen in time. However, we have motion in between the slices, and our job now is to kind of realign the slices again and come up with a 3D volume in the end. So we have 2D slices across different orientations, and we want to get a high-resolution 3D volume out of it. And this is exactly what classic methods have done for years, for decades. The problem is they're quite slow, so they can take several hours, and they're also not too robust. But what they do is they just align the slices to a 3D volume, they do super resolution, they refine the alignment, refine the super resolution over and over and over again. And recently there have been new approaches that do this a bit more efficiently and in an end-to-end manner, and they all drew inspiration from scene reconstruction. And I think most of you will probably have some understanding of scene reconstruction, and most of you probably can kind of like connect it to this nerve model, like neural radiance fields. And I would just draw the analogy between scene reconstruction and our fetal MRI real quickly here. So the idea of scene reconstruction is that we are provided with like 2D snapshots, like from your camera, of an underlying 3D scene, the drum kit here. And this is exactly what we have with our fetal MRI as well, right? Our 2D slices are basically our 2D snapshots. Our underlying 3D scene is the 3D brain. And we want to learn a model on these 2D snapshots, so our 2D slices, to consistently represent the underlying scene, which is our fetal brain. And as I said, like one method that does this is the nerves, like neural radiance fields. And here the idea is quite simple. You have an MLP, a multi-layer perceptron, and this one implicitly encodes the underlying scene, so either our drum kit or the fetal brain, in its weights by being fitted on these provided 2D snapshots, right? Well, the idea is, okay, let's use this approach, translate it to fetal SVR if it works that well, and hopefully we're faster and we're better. And this is exactly what we and others have done before. So this is kind of like, this has already been accomplished. It's kind of like old work, but it proved to be fast. It proved to set new state-of-the-art results. Well, so what did we do in this talk? Well, there's another method Gaussian splitting. Maybe some of you heard of it. It was quite big in 2020, or it was introduced in 2023 and got quite big. And the idea is, again, we want to represent an underlying scene, but we do it explicitly with these Gaussian primitives, like 3D Gaussian primitives that are splattered or rendered to a 2D snapshot, and they are compared to our provided views, and by this we can learn the underlying scene. So instead of implicitly representing the underlying scene with an MLP, we explicitly represent it with these Gaussian primitives. And, well, it was much faster than NERVs, and it proved at least as good of a reconstruction quality, if not better. So we thought, why not use this approach and translate it to fetal SVR as well? And yes, that actually worked. Otherwise, I wouldn't be here giving this talk. But the interesting thing is, it worked better than we expected. And to understand why, I want to quickly go a little bit into more detail of what is actually happening during the MRI acquisition. So you can see here in the top row, we have our fetal brain, or we have the fetus in the mother's womb. We put the mother into the MRI, we take the acquisition. And as I said, we take these 2D slices step by step by step, and we want to do it very fast, but the faster we acquire a slice, the less signal we have. And to compensate this, we increase the slice thickness, because then we can, again, get a stronger signal. But this results in very anisotropic slices, like, for example, 1 to 4 millimeters. And this acquisition blurs our actual underlying signal, and this is very important. So this blurring of the actual signal that you can see in the top row, the local row, this blurring is done by a so-called point spread function. So our sharp signal is in the end being blurred to a blurred signal. So if we acquire our slice, the slice is not like high resolution, it's rather this low resolution blurred slice. And from these slices, we want to reconstruct our 3D volume, right? This is here our end goal. In the scene reconstruction, it's the drum kit. Here it's our brain. And we have our forward model. That means we simulate this high resolution 3D volume. In the beginning, it's just random noise. We draw a high resolution slice. We simulate this blurring with the point spread function, which is a convolution of the point spread function over the high resolution slice. We get our simulated low resolution slice, and we compare it to the actual observation. We do this end to end until the thing has converged, and in the end, we will have learned our 3D brain. With the state of the art, this 3D brain, remember, is being represented with an MLP. We thought, let's represent it with Gaussian primitives. And here you can see what happens if we don't simulate the PSF. We get this result that is quite blurring. But if we consider the PSF in our forward model, we get a sharp and crisp reconstruction. So it's very important for us. And this is also the crux of our method. Let's first look at the state-of-the-art method with the MLPs. What do they do to simulate or to approximate PSF? Well, they have to approximate it with a Monte Carlo integration. So the convolution is quite, the integral is intractable, so they approximate it with a Monte Carlo integration, and for this they have to sample a lot of points. For each actual point, they have to sample like a neighborhood around it, dozens to hundreds of points, and then estimate like a weighted mean to get this actual convolution. And this, as you can imagine, is quite expensive. And if we look at our approach, we have our 3D volume, we draw this high resolution slice, and it's actually made up of these Gaussians, right? It's like a bunch of Gaussians, and together they represent the slice. That means our signal is a Gaussian, and the PSF is also modeled as a Gaussian. And the convolution of two Gaussians is again a Gaussian, simply with the covariance added together, the covariance matrices. So in the end, instead of doing this very expensive Monte Carlo integration, we just have a very easy addition of a matrix. So incredibly cheap, fast, and exact. And you can, like this manifests in a reconstruction speed, as you can see here, like on the top row, we have our state of the art, and at the bottom row, we have our proposed method, and you can see the reconstruction over time, and here the PSNR and the SSIM over time, and you can see that we like converge much, much faster. And to summarize, we are faster, we are at least as accurate. This provides us with some nice properties, like for example, during the MRI acquisition, sometimes some acquisitions turn out to be like of bad quality, there are image artifacts. With our method, you can like reconstruct right during the acquisition and see if you need to retake some slices to achieve a good reconstruction because it's so fast. So it's viable to do this during the clinical acquisition. And of course, like this principle, like slice to volume reconstruction is quite generic. It's a generic method, and this translates to any other domain, and especially to any domains that kind of like profit from the point spread function, like microscopy imaging. Last but not least, the team behind this work, I want to like thank especially Stephen Gia, who is one of the shared first authors from Marseille, and Neil, who provided me with a lot of ideas for this work. So it was like a collaboration of Marseille and Munich. And last but not least, the code is publicly available if you want to play around with it. And I'm happy to take your questions now, and any in-depth discussion, please come to the poster 116. I'm happy to talk with you. That's it.
All right, very nice talk, very impressive results. Apparently, we have a very eager question from the audience, so.
Okay, lovely talk, thank you. The one thing and this is more of a, I don't know the answer, and it's really a the nerf, as we heard yesterday, has one advantage of you can pool across subjects or across image stacks. So you can do some sort of meta learning in order to speed up the inference, but importantly, probably help the reconstruction quality as well, because you can sort of aggregate statistics that way. Is there a way to do that in the Gaussian splatting approach?
It's a very good question, and it's actually, I think, one of the major open fields in this, because there's not like a natural way to do this. You have to kind of have like a extra like meta model or something like the hyper networks in the INRs that learns the Gaussian representations. That'll be like via flow matching, diffusion, or whatever. But intrinsically, we don't have this. Like with the INRs, you can like plug in this latent code, and this is something we actually don't have with the Gaussians. Yeah. Thanks.
Okay, and quick question before we move to the next speaker that could get in line already. So you have very nice improvement in speeds, and that's mostly for your model. Do you still have, you think, let's say, low-hanging fruit in the hardware acceleration and implementation to make that even faster, or did you already push it to the limit, you think?
So the new results that you can see here on the last slide are actually updated. I think this is more or less close to the limit. It's like with the nearest neighbor approach, that for each Gaussians you don't consider the entire image, but just their like relevant neighborhood. But in the end, it's like hand coded. It's not like these highly optimized neural networks that you get from the normal frameworks. I think you can still squeeze out a little bit more of the optimization time here. And I think if you compare like the Gaussians and the pixels, the official approach is from Gaussian splatting, which is like a different framework, and it's officially available. I think they are even a little bit faster. But the thing is, there they have projections, right? You project the 3D Gaussians to 2D views to render it, and this is something we don't need in the medical field, or at least for the MRIs. And that's why we refrain from using it. But I think, like, if you have like a good software developer, you could still speed this thing up a bit. Yeah. Thanks.
Yeah, thank you very much. Let's thank the speaker again.
So now let us move the second presentation. The presentation title is Programmatic Nodes Evaluation Generative Model with Threshold Inception Distance for Retinal Image Synthesis by Yuli Wu.
All right. Good morning, everyone. My name is Yuli, and today I'd like to give a pragmatic note on evaluating generative models with Threshold Inception Distance, so FID, for retinal image synthesis. So this work was done during my affiliation with RWTH Aachen University and the University of Düsseldorf, both in Germany. All right, so in the biomedical context, when we want to use generative models to do something, one of the most primary use cases would be we want to use generative models to enhance the data set. So we want to generate more data. So given this general pipeline with a specific task with some real data set, we want to generate fake data and use the enhanced data set to do the same task again, but to improve the performance. If I quote from the good old book, Deep Learning, when they talk about evaluating generative models in 2016, I quote, "If we care about how well we can use the model in practice, then it is fair to say that a model is preferable based on a criterion specific to the practical task of interest." Sometime after that, FID has been proposed, so Threshold Inception Distance. It works like this. We have ImageNet pre-trained model, Inception v3, so it's a classic CNN model. And then we feed the images from the two datasets, the real dataset and the generated dataset, to this frozen model. And then we will have two sets of feature vectors. And then we will get the so-called Threshold distance with a huge assumption that these two probability distributions follow multivariate Gaussians. And in the paper, it shows that the difference of the two Gaussians, so the synthetic and the real-world images, is measured by the Threshold distance, also known as Wasserstein-2 distance. So with this, so since then, FID has become the standard metric to evaluate generative models because it's very easy to calculate. With the assumption of Gaussian, we can have a closed form calculation of the either Threshold distance or Wasserstein-2 distance. And after that, there are many the so-called FID variants or distance feature metrics belonging to this family. So basically we have different feature extractors to use other models, for example, large foundation models, CLEAP or Dino families, or maybe a in-domain pre-trained model, for example, RedFont in this case. So it's a image. It's a retinal image pre-trained foundation model. And we have different distances or divergences. For example, other than FID, also Threshold distance, we have MMD, maximum mean discrepancy, or maybe the KL divergence, and so on and so forth. And interestingly, each newer one would claim that they are more reliable than the previous ones and more robust. And in this paper, we'd like to verify that with the example of retinal images, following the general pipeline of using generative models to enhance the data sets. So here we generate synthetic data with a generative model, and then we calculate the evaluation metrics from the FID family, so to say. So FID, KID, CMMD, FLD, and so on and so forth. And on the other hand, we use the generated or enhanced dataset to do our downstream task. Depending if it's classification, then we calculate F1 score. If it's segmentation, we calculate DICE score, and so on and so forth. And here we tried two different retinal image modalities. So the retinal fundus, it's 2D color photographs of retinal surface, and retinal OCT, optical coherence tomography. So with OCT, we can see the 3D layered cross-sectional structure. And also we tried different generative models, for example, StyleGAN V3 from GAN family, or DDPM from diffusion family. And here are some results. So we first analyzed the features from the feature extractors in terms of the sparsity and the entropy. So here we have the hypothesis that the in-domain models, so in this case we refer to the REDFound model because it's a retinal image pre-trained foundation model. So these in-domain models should be more sparse and should have higher entropy. But you can see from the figures that it's not the case. And on the right side, it's one of the experiments. So it's a diffusion model on OCT generation, and the downstream task is the layer segmentation. So the hypothesis, again, is that we assume that all curves should show very similar trends, meaning that the dye score and FID, so here we use 1 over FID to show the same trend, they should align with each other. So at the beginning, it's kind of true, but then maybe in the extreme case of the last model, so the DM7, we can see that if we follow FID to pick the model, for example, the model with your new parameters, or maybe just if you pick the number of the epoch or the checkpoint based on the FID, so there's a chance that you actually pick the worst model in terms of the downstream performance. Some more experiments. So here on the left are rectangular matrices. So we calculated the candles tau rank correlations. Because they claim they are better than the previous ones, more reliable, but it turned out that they are not too different. So we expect to see some differences in terms of the ranking, but they are actually very similar. So the conclusion within our experiments is that the FID and FID variants are not better than the FID. If we check the last column, so we also calculated the candles tau rank correlations between the FID family and also the downstream performance, so the utility here. So the ideal correlation would be -1 because FID and FID family would be the lower the better, and the downstream performance, so F1 score or dye score, the higher the better. So the ideal correlation would be -1, but you can see here is that the base case would be only -0.43, so it's far from -1. So we can draw the conclusion here is that so the FID family, they rarely align with the downstream performance. With that, I'd like to give a short takeaway message is that just use the downstream task performance rather than FID when evaluating biomedical generative models. Maybe it's not limited to biomedical models, but with our experiments, we draw a narrow conclusion. So yeah, just go back to the original idea of just using the downstream task because it's risky if you follow the FID. Maybe you can pick the worst model. Yeah, so on the left you can see more figures, tables, data from our paper, more experiments. And on the right side, if you are interested in Fréchet distances, so here is a kind of review of Fréchet distances. So actually it's originally for the curves. So, and then Fréchet proposed another distance for probability loss or probability distributions. And here we draw the conclusion, we draw the connection between the two and also show the development to FID. Yeah, with that, I'd like to thank you very much for your attention, and I'm happy to answer your questions.
The session is open for question. Or maybe I can start. Oh, yeah, go ahead.
Hi there. Thank you so much for your talk. Very interesting. My question would be the following. So, as I see, like as many papers come out recently, there's a whole spectrum of evaluation metrics for generative models. Like we go from distributional metrics like FID and their variance to more semantic metrics like clip score or whatever. And then on the other end of the spectrum, we have the downstream task performance. So my question is, should we really be that absolute that only downstream performance is an important thing, or is there something that downstream performance does not capture and maybe we get it from other metrics as well?
Yeah. So the question is, maybe there's something between the FID and downstream task which can do the job. Is that the question? Okay. Yeah. So we are looking for some kind of better distances, maybe the characteristic functions, that family, to calculate the distribution in a frequency domain, complex domain, and maybe to have a more powerful feature extractor, larger model, more general model, for example. Or maybe we can just follow the approach maybe in the hyperparameter tuning where we just run the model for a very short number of epochs with a subset of the data, kind of a mini downstream task performance check. But only from the like a pure metric perspective, I'm not aware if there's anything that would be good enough. So do you have suggestions for that, maybe?
No, we can discuss later. I think like the first thing that pops to mind is the fact that diversity is an interesting thing to evaluate generative metrics. I'm not quite sure if downstream performance captures that, right?
Yeah, so we also did the calculation of precision and recall. It's the same as FID. So in a way that if FID is calculated correctly, or it can represent the distribution, then it's not too far away from diversity and coverage, for example. I mean, it becomes maybe a more general question that what kind of data we need to have a better result, kind of coverage stuff, the difference between the training data and the test set. So.
Thanks so much.
Right, thank you.
Okay, maybe another quick question. So correct me if I'm wrong. So how can you evaluate your synthesis data diversities? Because you can generate all kinds of image, right? How can you evaluate diversities?
So normally just in the latent space, we have a feature extractor or a pre-trained model. We just have a feature vector from a piece of data, an image, and then we just calculate some statistics among the feature vectors.
Okay. Thank you. Let us thank the speaker again.
Yeah, thank you.
All right, and so if our third speaker could appear. Okay, so our next talk is entitled Vector Quantization for Reverse Disease Progression, Further Investigation by Chi-Chi Chen. And now the floor is yours. You have 10 minutes.
Thank you. Thank you so much. It's my pleasure to be present here. And today I want to present our work, Vector Quantization for Reverse Disease Progression, Filter Investigation. And it's a joint work with Changfu Guo in Chang'an Memorial Hospital. So when I'm interested in a kind of disease called midnight shift quantification, and I show in the image, the midnight shift distance is the largest distance between the blue and the red lines. And I mean, it's a very simple test once we have a segmentation model. For example, they can segment your left brain and right brain. But what I want to emphasize is that just data annotation is just time consuming. So in this work, we try to think about what can we do if we just have no segmentation, but we just have classification model, classification label. I'm sorry. So we propose to use risk supervised learning to address this issue. So first, we use a generating model to generate the normal counterpart of the original image, and then estimate the deformation field by image registration. And furthermore, we hope the reconstruct image is unbiased in the sense that only page linked to the midnight shift are altered. I mean, we don't want to change too many areas. So for generating model, the most common approach may be using latent diffusion model plus classifier free guidance. However, in this work, we try to investigate something different. We try to use the latent formation model, and as a byproduct, we can simulate the image in each time step. So we call it reverse disease progress. So here's the pseudocode for latent formation model. For latent formation model, the source distribution is not limited to normal distribution. So in our case, we use all CT image as our source distribution and use CT image without midnight shift as our target distribution. So it's possible that the latent formation model just, let's say, conceptually equivalent to latent formation diffusion model. It's possible. I didn't think too much about that. But let's try to look at loss objective. I think it's more straightforward in the sense that in each iteration, we need to pick pair of elements from the source and target distribution and find a difference vector and use this vector to train the network to predict the trajectory at time step t. So, but that's the first problem we encountered, and we really want to appreciate the reviewers' comments since we didn't notice that before. So, for latent formation model, if we use VAE as our autoencoder, and we found even the normal images, there's some tiny variation around the ventricle. So if we want to directly use image registration then the estimation error will be higher. So I test several kinds of autoencoders. So I found one autoencoder called OPTVQ. Performance is promising, and I will introduce now. So let's briefly review the VQ model. So for VQVAE, let's co-boot in the latent space, and the page in the latent output is assigned to the nearest code in the code book. And one of the loss objectives is try to minimize the mean square error between the page and their assigned codes. But if we think about the loss objective more, it means that for the code select in this A part, it's more likely to be selected in the next A part. Even if you have huge code book, the code book utility rate may be very low, so which limits the representation power. And in these 2 years, there are many proposals to, and I'm interested in this kind of model called OPTVQ, OPT for optimal transport. So in sum, we still want to minimize the mean square error between these pages and their assigned code, but under the constraint that the transport map in the latent space should be only transport from the source distribution to target to the code book. So it cannot just send it to the same point as the industry here. So for OPTVQ, it uses a kind of famous approximation algorithm called Sikov-Knop iterations. Maybe we skip the technical detail, but what I want to emphasize is, in general, it requires around hundreds of iterations for convergence, but the default setting of OPTVQ is just 5 iterations. So it's hard to say it really converges, but in practice, I found the image quality is good and the corporate utility rate is high. So this is the second problem. We found that no matter what kind of autoencoder we use, it's just really hard to preserve hemorrhagic regions. So in some sense, that's right. I mean, we still reconstruct the image without midnight shift, but most of the time, the midnight shift distance is caused by such hemorrhagic region. But sometimes we'll just ask, could we do better in the sense that could we preserve such regions if it's not related to, midnight shift distance, this disease. So we don't have a good solution, but we can share some of our experience in this talk. So the first observation is we inspired by the mask autoencoder. We just randomly preserve 50% of pages and substituting the 85% of pages by the average pixel value. Of course, we didn't train the mask autoencoder, so we cannot expect it behave at that way. But we found that both VAE and OVTVQ reconstruct the preserve, the 50% page really well. But one thing I found is really interesting is that for OVTVQ, it can really reconstruct pages with average pixel value. It's not exist in the training data set. So that's one reason I think maybe I should investigate is this kind of model filter. And the second idea is we want to apply cost-missing observation in the latent space. So we just do the experiment, given a pair image, and we pass through the encoder, and we just crop regions around ventricles, and shuffle these regions and pass it to the output, pass it to the decoder. And we found that in general, BQ model produce fewer artifacts than VAE. So that's the reason why finally we choose the BQ model. And but from these two observations, we found that there's a strong spatial correlation between the pixel space and the latent space. So we have some 3 proposals to preserve the hemorrhagic region. So the first idea is really naive. So when we train in the formation model, so you see the source image and the target image. So when we train the latent formation model, we just pick some latent vectors corresponding to the high intensity area in the source image and just shuffle to target image. So we just do that kind of convention in the latent space. So, and the second idea is that we try to modify the unit architecture in the formation model such that there's additional branch to predict deformation field, but in the latent space, not pixel space. And finally, we try to, since we are into our interest areas around the ventricle. So after we apply the formation model, we just preserve the regions around the ventricle, and we just replace all other latent vectors with original latent vectors. So, here I can show some results. So for results, we can see that our second method, the OPTVQ and with our modified unit architecture performs best. But another thing I want to mention that so far we didn't perform well at cases with large midnight shift distance, and I will discuss it in a very short time. So, and we can show some results. So we found that combining the first and the third method preserve the hemorrhagic region best. So maybe I skip this part, but I can talk it post-session. So in conclusion, we try to conduct investigation on controlling such trajectory from CT image to midnight shift to normal image. And we know there are some limitations, but we want to invest in the future. And any idea, comments, and I'm happy to answer it now. Thank you so much.
Right. We have another eager question. Please be quick with the answer still, but yeah.
Okay. The question I have is, the generative model that you use is generating pixel values directly? The flow
I work in latent space, so I need.
sorry, in latent space, but you're actually generating the image intensities. But the problem you're interested in trying to characterize is a geometric distortion problem. So midline shift is a geometry problem.
Yes.
So have you thought about generating the deformation directly? I know you did some warp thing, but I'm not sure if that was exactly what I'm thinking.
Yeah, I know what you mean. So far, honestly, so far I didn't try it. I mean, I was
Because it wouldn't, I mean, the hemorrhage, for example, would be preserved, right? Because
Yes.
right. So a lot of your issues that you're trying to address through, the subsequent additions to the latent diffusion model, I think you could just, if you generated the deformation directly instead of pixel values directly and then applied it, I think you could fix some of those issues. Does that make sense?
Yes. I mean, I also need to say I didn't try it, but I will try it. Thank you so much.
Thank you.
Thank you.
All right, and I have quick question for maybe, I think quick answer doable. You use data from your own hospital.
Yes.
So I have two questions related. Over how much time was that data collected? And do you have plans to test with data from another site to assess how your method generalize?
Could you say it again? I'm sorry, could you say it again?
Oh, yeah. Over how long, how much time was the data from your hospital collected? Was it 1 year, 10 years, 20 years? And do you have plans to test with data from another site?
Oh, you mean label?
Yeah, or even the images, they all come from the same place. So
Yes. Yeah, but I know that the images are coming from the same hospital. I mean, I also combined some image from the ISN dataset released in 2019. So I think maybe what you worry about is the overfitting issue, but I think from my observation, the main point is that for so far the limitation of our algorithm is that it doesn't perform well when the midline shift is large. I'm sorry, but I will try. What I want to say is that maybe let's not overfitting, but maybe we need to adjust our strategy. I mean, I think there's a better way to handle this. Yeah, I still have some limitation here.
Let's thank you very much, and let's thank again the speaker.
Okay, our last oral presentation is the presentation title is Anatomy Grounded Weakly Supervised Problem Tuning for Chest X-ray Natural Diffusion Model by Constantinos Vinoris. Please correct me if I'm pronouncing it wrong for your name. Sorry.
No, that's fine, thank you. Yeah, good morning everyone. My name is Konstantinos. I'm a PhD student at the University of Edinburgh. And today I'm going to present your paper called Anatomy Grounded Weakly Supervised Problem Tuning for Chest X-ray Related Diffusion Models. Right, so there was this idea that popped up a couple of years ago saying that we can actually get a pre-trained text-to-image latent diffusion model and repurpose it for various downstream tasks, which I find quite fascinating because it sort of challenges the classic paradigm of having a task-specific model every single time. So yeah, there have been many papers published recently that show that for various tasks in the general computer vision domain. However, this is relatively underexplored in the medical imaging domain, where there are only a couple of papers showing that in terms of classification and phrase grounding. So for those who are not familiar, the task of phrase grounding is essentially the mapping of a text description onto the region of the image that sort of aligns with what's said in the text. So for example, if we're given a prompt that describes the findings of a medical image, then the model should output a heat pump that should activate only around the region where the finding is present. So we have worked in the past on phrase grounding a lot. So we developed a method that can solve this task in zero shot, which performs fairly well. However, there are a couple of issues that arise. So the first one is a thing that is called attention leakage, which essentially means that image text alignment, the pre-trained data diffusion model is kind of poor quality. And it's shown in the heat maps that you see on the right side. So in that sense, one could argue that this issue can be attributed to the complexity of the text prompt, because it's essentially a sentence that we extract from the radiology report. However, we test that, we get more simplified prompts for that, and this is not the case. This does not explain what's going wrong. However, the good thing here is that we can solve this issue post hoc by having a small data set that we can fine-tune our model on and improve alignment, which brings us to the second issue: we have no training data. So in that sense, in this work, our contributions are the following. So at first, we have to come up with a fine-tuned data set. So we come up with this data curation pipeline to extract like weak phrase ground supervision. And then we also propose an efficient fine-tuning framework to improve this alignment. So first, for the data curation part, here we essentially want to focus on the anatomy aspect of things. So in that sense, we leverage existing anatomical annotations from a data set called chest image genome, which essentially provide a bounding box per an anatomical area that's commonly depicted in the chest X-ray. So per region, we aggregate all those bounding boxes and we turn them into a Gaussian, as we can see in the figure on the right, which gives us a dictionary with keys being the anatomical regions and values being the corresponding Gaussians. And then, given the subset of the data that we use to pre-train the diffusion model, we focus on the radiology reports, we identify the sentence that refers to the pathology, and then we use a pre-trained clinical entity recognition model to identify the tokens that refer to anatomy. So in that sense, after we extract those anatomy-related tokens, we can use those to find the corresponding keys from the dictionary that we constructed previously, and then get the corresponding Gaussian. So in that sense, we now have triplets of an image, a text prompt, and a weak supervision signal in the form of a 2D Gaussian. Then, in terms of the actual fine-tuning, things are very simple. Essentially, most of the model remains frozen, and the only thing that we update are the anatomy-related token embeddings. And we had to come up with a loss function that enforces this behavior. So, yeah, the loss function consists of two terms. The first one, which is straightforward, is the localization loss, which guides the model to output cross-attention activations that are as close to the Gaussian as possible. And then we also had to come up with a regularization term called diversity loss here, to avoid any trivial solution. So in that sense, we say, okay, we might have more than one anatomy-related tokens. Please try to come up with a different representation for each token. So in terms of the quantitative results, we use an existing phrase grounding benchmark, which is a subset of mimic CXR. And our fine-tuned model, which is the purple bar in all cases, performs very well. It has new state-of-the-art results. And we also try to see whether this whole pipeline generalizes to out-of-distribution imaging data. Therefore, we use the images from VinDoctor, CXR, and we come up with synthetic prompts in this case because we don't have access to radiology reports. And thankfully, we also see generalization to these OD images as well. Then we decided to conduct a small-scale qualitative study involving two radiologists. And the idea here is to see whether the improvements that we see in terms of downstream metrics are also reflected by the decision, or like the scores that radiologists assign to the heat maps. So yeah, what we did is that we extracted multiple heat maps, we gave them to the radiologists who kindly offered to help, and we asked them to score each heat map on a 5-point Likert scale. And yeah, the original hypothesis that we had was also verified, so we see that there is a significant correlation between the improvements in quantitative metrics and the improvements in the radiology scores, with a metric called contrast to noise ratio being more closely aligned to what the radiologists have to say. And the last thing is that we also wanted to show the downstream utility of having more accurate heat maps. So in that sense, we had to come up with an exploratory setting to test that. Right, so here we leverage an existing method that repurposes a diffusion model for classification in zero-shot. And we observe the following. So this method comes up with a classification objective that operates on the output of the denoising unit, which is like a spatial signal, like the noise or the velocity. And here we observe that since this is a spatial signal, then we can also use some sort of external spatial guidance to guide this network. So in that sense, we thought of coming up with a grounded classification task where we split things into two stages. In the first stage, we extract a heat map, as we have done so far, and then we apply the heat map to the output of the diffusion model so that we can make classification decisions within the region specified by the heat map. And since we defined this task, we wanted to test the hypothesis that having more accurate localization also translates into improved grounded classification performance, which again, thankfully, seems to be the case with statistical significance. Yeah, to sum things up, we mentioned here multiple issues related to the poor image text alignment in pre-trained text image latent diffusion models, and we came up with this novel weakly supervised framework to address this issue. And the key result is robust generalization to out-of-distribution images, and the fact that the gains in metrics that we observe are also statistically significant and also align with what expert radiologists have to say. And the last thing I want to mention is that for people around here working with MRI and CT modalities, given that you bring your own anatomical atlas and your own latent diffusion model, the rest of the pipeline can also expand your use case as well, which would be very interesting to see if it actually works. Yep, so feel free to bookmark our project page for more details. Other than that, please join me in the poster session to have more in-depth discussion. So, yeah, thank you.
The session is open for question. Or maybe I can start. Very nice work. So, let's work for the 2D X-ray image, right? Do you think, can you comment if in future we want to use for 3D? We have a lot of 3D CT scan, right? Do you have any suggestion, comments? If in future we want to apply this kind of model for the 3D image, what should we do?
Right, so I will start by first by the heat map extraction stage. So the whole method that we came up with to come up with heat map extraction does not really depend on the type of input modality. So I believe, I haven't tested it myself, but I believe that we can extract heat maps from a 3D latent diffusion model in a similar way. The only thing that makes things more complicated is the time aspect or the additional dimension that we have to say in general. And then what I mentioned in the end is that, yeah, of course, this work focuses on chest X-rays in the sense that we leverage an anatomical atlas for chest X-rays, and also we have the chest X-ray latent diffusion model. However, the clinical entity recognition model that we use is also trained to reports coming from CT and MRI, which is why I said that technically speaking, it should work. yeah, if anyone's interested, I'm down to see if I generalize as well. So in general, I think it should be fine.
Okay. Yeah.
Thank you very much for this interesting talk. I come from the radiotherapy topic, and we have sometimes a hard time locating lung tumors. So with your model, do you think you can know if there's a lung tumor and so locate it?
That's a very good question. So I think we can blame the phrase grounding task for my answer. The thing is that for a phrase grounding model to work, we need both an image and a text description. So that means that we know already that something is there, and we ask the model to just localize what's happening. However, as I also reflected after this work was published, we need to come up with better ways to perform grounding. We need to account for cases where there's uncertainty behind all that, or the fact that everything might be okay, like the patient might be healthy, therefore the heat map should not activate pretty much anywhere, right? So yeah, there's this current limitation that is not really addressed in any domain, but yeah, there has to be something, and you need to specify it in text. If you satisfy this assumption, I assume that it should work, especially in the case when you don't have any training data, like you want something to work off the shelf. So assuming you have a latent diffusion model on the modality that you're working with, it should do something.
Okay, let us speak again. If you have additional questions, you can talk with Arthur in the post session.
All right, and now we will have 4 pre-recorded spotlights. The presenters are actually not pre-recorded. They will be actually presenting live in 3D after, so please bear with us. So the first one is about evaluation of 3D ultrasounds, reconstruction, and 2D, 3D segmentation for neonatal hip dysplasia screening. Hopefully she doesn't say the title again, and yeah, please watch it attentively.
Welcome to my spotlight on 3-dimensional ultrasound reconstruction and 2D, 3D segmentation for neonatal hip dysplasia screening. Developmental dysplasia hip is the most common musculoskeletal disorder in newborns. It describes an abnormal development of the hip joint, and early diagnosis can prevent surgery in adulthood. Today, screening is mainly based on the Graph method, which uses a single manually aligned 2-dimensional ultrasound frame. However, the hip is a complex 3-dimensional structure. Reducing it to a single slice makes diagnosis highly dependent on probe positioning and operator experience. Since the current workflow is based on angle measurement to landmark identification, small changes in probe orientation can directly affect diagnosis. To mitigate this, we investigate whether freehand ultrasound reconstruction combined with segmentation can provide a comprehensive 3D representation of the hip to enable retrospective analysis and potentially more robust diagnostic measurements. Our pipeline starts with 2D ultrasound frames extracted from freehand sweeps. We annotate a subset of these frames and train segmentation models in 2D. These segmentations are reconstructed along the images into volumetric representations. After 3D refinement, these reconstructions are used to train volumetric segmentation models. This iterative loop allows us to progressively improve consistency while significantly reducing manual annotation effort. We collected a large multi-center dataset with over 1,000 neonatal hip ultrasound sweeps acquired during routine clinical screening. This includes standard graph views as well as additional freehand sweeps capturing complementary anatomical directions. For a subset of the data, we also have optical tracking information, which provides ground truth trajectories for evaluating reconstruction quality. We manually annotated more than 600 frames and trained 3 2D and in-unit segmentation models, while each time iteratively refining the annotations. While 2D models achieve reasonable performance on individual frames, they often struggle to produce anatomically consistent 3D structures. For 3D reconstruction, we trained an image-based model to predict frame-to-frame motion and included optical flow and IMU data. Reconstruction trajectories closely follow the tracked reference trajectories, enabling realistic volumetric representations of the hip. This example shows the progression from slice-wise predictions to coherent volumetric models. We observe that iterative refinement significantly improves smoothness and anatomical plausibility of these segmentations. Quantitatively, we see a clear improvement in the segmentation performance, with mean dice-scores increasing from around 60% for 2D-based reconstructions to over 80% in the final 3D models. Overall, our results show that incorporating 3D context leads to substantially more robust segmentation and better anatomical consistency. We believe this is an important step towards more reliable ultrasound-based screening for DDH, and we are currently extending this work towards clinical evaluation of 3D-derived diagnostic metrics. I look forward to discussing this at our poster.
Okay, our second presentation is from Yucheng Yang.
Hello, I'm Yucheng Yang. This video is about our work, explainable Pathomix feature visualization via correlation-aware conditional feature editing. Most conditional diffusion methods implicitly assume that the features they edit are independent, such as the stem length and the size of an apple. However, in the field of Pathomix, features are often correlated. For example, the area and the parameter of a nucleus. So the goal of our project is to make the model aware of such feature correlation and generate feasible edited images. This slide illustrates our core motivation. The surface represents the manifold of real feature space. Existing independent editing moves directly towards the target feature value, but this can push the condition of the manifold and produce unrealistic images. Our idea is to perform manifold-aware editing, which is to allow correlated features to change along the manifold. This slide shows our main model architecture. Given an input image and a target feature value, we first encode the original feature vector into the VAE latent space as the starting point for optimization. Then we optimize the latent code to make the decoded feature vector move towards the target while still staying on the learned feature manifold. The resulting optimized feature will finally use to condition the diffusion model and generate the edited images. Here are some of our qualitative results. For stable diffusion and MAD without the VAE, the edited images remain very similar to input nucleus across the whole target trajectory. This suggests that when the feature condition is conflicting, the methods are not able to correctly respond. In constructs, as the target feature changes, MAD can respond to the target editing direction accordingly, while still preserving the overall nuclear appearance. For the quantitative results, MAD achieves the segmentation success rate of 99%. It also achieves the lowest MAE and the highest R-squared value. To conclude, MAD enables feature-guided image editing under correlated feature conditions while avoiding unrealistic results. Here are the link of the paper and my contact information, and the code will be released soon. Thank you for your listening.
And the next spotlight is by Raja Kashmi Palaniappan.
Hi everyone, I am Rajalakshmi Palaniappan and I will be presenting our work vessel post, vessel graph reconstruction from learned voxel-based direction vectors in 3D vascular images. Why do we care about graph-based reconstruction? Because it converts complex vascular images into simplified graphs, enabling quantitative analysis and thereby can support applications such as establishing organocatalysis, flow simulations and also in diagnostics. Currently, most existing methods still follow a segment then skeletonize strategy. This can work in simple cases but often fails when vessels are faint, disconnected or very close to each other. In such cases, segmentation error directly becomes topological errors. To address this, we introduce vessel post, a two-stage pipeline for vessel graph reconstruction. The key idea is that a binary foreground mask alone is not sufficient to resolve vessel topology. Therefore, our 3D unit predicts both the vessel foreground mask and voxel-based direction vectors. These predictions are then passed to a modified teaser for graph extraction, followed by hierarchical matching for evaluation. Here is the intuition behind our modified teaser. Standard teaser mainly traces skeletons based on distance from the object boundary, which can be ambiguous when the vessels are spatially close. In our method, teaser is guided by predicted direction vectors. These vectors point towards the vessel center line and are biased towards the root of the tree, giving each voxel local information about where the vessel should continue. We also support multiple routes within one connected component, which is important for real-world multi-tree dataset. A second contribution is our evaluation framework. Comparing vessel graphs is difficult because a single incorrect edge can have very different topological impact depending on where it occurs. Therefore, we use a topology-aware hierarchical matching strategy. Based on this matching, we report two intuitive topological errors, false merges and false splits. A false merge is a predicted edge connecting two nodes that are unrelated in the ground truth, meaning neither node is an ancestor of the other. Here, this is a false merge. After removing all false merges, any increase in connected components is counted as false splits. So false merges capture incorrect connections while false splits capture broken connectivity. We evaluated vessel pose on both synthetic single tree dataset and pulmonary artery dataset. In both cases, vessel pose outperforms the baseline in point level and branch level F1. We also evaluated on a multi-tree synthetic dataset where preserving separate vessel is more challenging. Here also vessel pose improves edge F1 and reduces false merges and false splits. Qualitatively, vessel pose preserves most of the separate tree structures, while unit with regular teaser incorrectly merges many vessels into one connected component. Finally, we evaluated on the more challenging micro-CT dataset. Here again, vessel pose outperforms the unit plus regular teaser baseline. Visually, the baseline misses several vessel regions, while vessel pose recovers a more complete vessel prediction. Overall, our results show that predicting direction vectors rather than relying on segmentation alone enables more topologically accurate vessel graph reconstruction. The code is available on GitHub through the QR code, and we would be happy to discuss more at our poster. Thank you.
Our last spotlight is from Solid Belgium.
Good morning, I'm Laura Solard, and this is the spotlight presentation for Endo4DTS. The objective of this research was to extend the triangle splatting approach, originally designed for rigid 3D scene reconstruction, to work in deformable scenes, specifically in endoscopy videos with a monocular camera. To the best of our knowledge, we are the first ones to extend triangle splatting to deformable scenes and also the first ones to propose its application in endoscopy settings. Triangle splatting is quite similar to 3D Gaussian splatting, which some of you might be familiar with, but it uses triangles as primitives instead of Gaussians. Traditionally, splatting methods use a point cloud obtained through structure for motion to initialize the scene. However, these methods fail under deformable environments, and endoscopy settings make it even harder for them to work. So we decided to use the first frame of an endoscopy video with a static camera, together with a monocular depth estimator, to initialize the triangles into what we call a canonical space, which is a static. Then, this canonical representation is jointly optimized with a temporally aware deformation network that estimates the rotation, translation, scale, and color changes of these canonical triangles into a deformed space. With this, we can obtain a deformed state of the triangles for each frame of the video, which we then use to render new images through differentiable rasterization. We propose several additional loss terms to further regularize the solution. First, a depth loss between the input and render depth maps, and a depth smoothness loss to enforce neighboring pixels to have similar depth values. We then add a rotation and translation regularization to avoid large deformations. And finally, a position consistency loss to encourage triangles that are close in the canonical space to remain similarly close after deformation, promoting coherent local movements. So after performing an ablation study on the different loss terms and also a sensitivity study on the strength of some of those terms, our final method consistently outperforms all previous methods on the EndoNerve dataset. We also tested 2 additional datasets to further demonstrate the generalization capabilities of our Endo4DTS. As you can see, we also outperform other methods that have used these datasets. Here you can see the results for the pulling sequence on the EndoNerve dataset, and here the cutting sequence. As you can see, we capture in great detail all the small vessels, the texture of the tissue, the specularities, and the pulling and cutting of the tissue. So, if you want to know more about this method, please seek me out at the next poster session. Thank you very much for your attention.
And that was it for this session. Thank you everyone for your attention. We have a few minutes until our next great keynote, so you can go out, stretch your legs. Don't forget to drink water, but please be here on time.
Mert Svenshu to give the keynote. So Professor Mert Svenshu is a professor of electrical and computer engineering at Cornell University and Cornell Tech, with dual appointments in radiology at Weill Cornell Medicine, where he served as the vice chair of AI and engineering research. His research focused on the development of machine learning-based computational methods for biomedical imaging, spanning image acquisition, segmentation, multimodal data integration, and clinical translation. And Prof. Mert has received an NIH Early Career Development Award and an SF Career Award, and he served as editor-in-chief of Member, machine learning for biomedical image analysis. So today, he will give the talk about beyond the benchmark, building AI that has an impact. So let's welcome Professor Mert to the talk.
All right, good morning. This feels very weird to hold up a microphone like this, so sorry if I can't walk around. But thanks for being here, and thanks, Yumin, for the kind introduction. It's lovely to be at MIDL. It's my first MIDL. I tried to come once a couple of years ago and couldn't make it because of travel, canceled flights and whatnot. But I'm glad I could make it out this year, and I really enjoyed all the talks and learned a lot and been inspired. So today I'm gonna give, since it's a keynote, I took creative license. And I decided to not be super technical. So the talk is not going to have a lot of technical content. Hopefully, you'll be able to follow. The messages are very, very simple, and I don't have that many. So hopefully, you'll come away with the ideas that I'm trying to convey. But obviously, at the end, if you have any questions, feel free to just ask questions like I did. You can go up to the microphones. So before I dive in, I advise a bunch of companies. Two are relevant. One's clearly a startup that came out of Cornell, about 10 years old now, works in the space of AI and CCTAs or cardiac CTAs. Another one is MIDL, which is also a Cornell Tech startup that works in breast cancer risk prediction based on mammograms and breast MRIs. The other thing I wanted to point out is I'm the editor-in-chief for MELBA, the Journal for Machine Learning for Biomedical Imaging. MELBA and MIDL have this special relationship, and we have a special session this afternoon that's dedicated to MELBA papers that I encourage you to check out. It's an oral session, and I'll also talk a little bit about MELBA, the journal's mission, and what we're trying to do with it in that session, at the beginning of that session, very briefly. Okay, so I'm going to start with a quote that is about 10 years old at this point, and I'm guessing many of you, if not all of you, have heard of it. And I'm guessing that all of you know who this person is, Jeff Hinton, who's kind of, at this point, a Nobel, like he has everything that you can probably win at this point, right? He's a Nobel laureate, he won the Turing Prize, he's maybe the top-cited scholar ever, and, the father or godfather of deep learning. And he made this famous prediction about 10 years ago in his hometown in Toronto, where he basically stated that we should, radiology is dead as we know it. Deep learning is just going to come and take over radiology, and we should just stop training radiologists. And everything that radiologists do today can be automated, basically, with deep learning algorithms. Obviously, almost 10 years have passed, and radiology is alive and kicking. And importantly, it's actually, quite the opposite, right? We more than ever need more radiologists. And so deep learning definitely has not automated radiology. And there's many reasons for that, and I'm going to sort of try to explain some of those reasons in this talk. So if you've ever, gone to a radiology reading room, observed radiologists, or some of you might actually be radiologists in this audience, or if you've observed radiologists at work, you will realize that they're often sitting in this dark room in front of these giant screens, scrolling through images. They're working under time pressure. They usually have 5 minutes, 10 minutes, 15 minutes to read an MRI scan or a CT scan that has millions and millions of pixels, hundreds of slices or images that they have to go through. This is a life or death, literally, task, right? The patient's life is at stake, or health is at stake at the very least. There's a lot of uncertainty that they're dealing with. There's legal liability on the line. They're just drowning in volume. The amount of pixels that radiologists have to read is growing very, very fast. We're acquiring more data, higher resolution images, and we're not training more radiologists. In fact, in most US institutions, medical schools, radiologist residency programs haven't grown in the last 2.5 decades at all. So something's got to give. And in my mind, and many people would agree, I hope, that AI is going to come to the rescue. And the way it's going to come to the rescue is, first of all, the technology has really, really taken off, as we all very well know at this point, right? We have these amazing models that have amazing capabilities that are trained on these ginormous data sets and show amazing promise, right? But the fact of the matter is, at least at this point in time, much of that progress hasn't really translated into the radiology reading room. Clinical adoption, more broadly, even beyond radiology, has remained very fragmented in healthcare and medicine. Things are changing, but changing very slowly. And, the question is, what is the explanation of that slow progress, right? What's the disconnect between the amazing potential these AI models are showing on our data in our papers versus what's going on in the radiology reading room? Okay, so a lot of the AI progress has obviously been fueled by data, and benchmarks, these sort of competitions where there's these benchmark data sets, play an important role in all of this, right? So these benchmarks and these competitions essentially allow us to share data, or incentivize us to share data across the community, draw attention, resources, and talent to a specific problem of interest, right? I'm guessing a lot of you in this room have worked on brain tumor segmentation, even though you've probably personally not been, associated with a brain tumor sort of collaborator, right? And the reason you've worked on that problem is there's a data set out there, or there's challenges out there that sort of allow you to take this problem and apply your ideas to it and make progress on it in an objective, measurable way. And so benchmarks are great at that, right? So it basically allows us to, have lots of different people across the world bring their talent to a specific problem, work on it, and make progress on that problem. And we measure our progress. And this is not just for medical imaging. Obviously, all of machine learning has really benefited from this kind of framework. You think about the ImageNet challenge, for example, the benchmark, right? That fueled most of the early computer vision work in deep learning. But we also know that, benchmarks often have a short lifespan before they actually saturate. Broadly in machine learning nowadays, the lifespan could be in a matter of months. Like within 6 months, a benchmark could be outdated, just solved basically for all practical purposes. So we sort of constantly are facing this dilemma of like, okay, what's the next benchmark? What's the next benchmark, right? Once we solve it. But relevant to this sort of talk, I guess, is and I think more importantly that, the performance measures on these benchmarks, right, that we are sort of hyper fixating on, really often have little to do with the practical value or the practical impact of these models, okay? So, if you take a segmentation challenge and look at its leaderboard today, DICE metric, which is your go-to segmentation quality performance metric, would be a primary thing you could focus on to rank order the AI models in terms of how they're performing. You'll basically see that a lot of the top performing ones will have a very similar DICE score. And the fact of the matter is, for practical purposes, those models are not that different. They're all going to basically be the same in practice when you deploy them. And DICE is not the right metric to hyper focus on in terms of trying to figure out which one's better than the other one. Okay, so my thesis in this talk, and this is the only thing you need to remember, and I'll give you some evidence for this thesis, I guess, is I don't think AI models that are on top of these leaderboards that give you, 0.01% improvement over the second model per se, are the ones that are going to transform radiology or more broadly medicine. I think what's going to really transform radiology are AI systems, not just specific models, but models working together in systems, plugging into the IT infrastructure, interfacing with humans, that are actually useful, robust, and reliable. And usefulness and robustness and reliability obviously have very specific meanings here that I'm going to try to make concrete. Will be the ones that will have impact in radiology and transform radiology. Okay, so this will be a very sort of I'll tell you two stories from our research. They're not the most technically sophisticated stories, to be frank, but I think they're good examples of to make my points concrete. And the first story I start with. So in part one, we'll take on this sort of problem of measurement. Okay, and in physics, measurement is always often thought about as one of the most interesting problems. From an algorithmic standpoint, it's not the most exciting question to focus on. And when I talk about measurement, what I mean by that is essentially literally physically measuring the width, the length, the depth, the area, the volume of structures of interest in our pixels, right? So basically identifying the boundaries of an object and coming out with a geometric measurement of, say, the circumference, or counting objects. So these are quantitative measurements that you can obtain from the contents of your pixels. And to some extent it's not, it seems like a basic question, but it's, in my mind, the lowest hanging fruit for AI to actually transform radiology. And I'm going to really try to sort of make that concrete in a very specific disease context that I've been working on, or with my collaborators and my students and colleagues. This is a disease called autosomal dominant polycystic kidney disease, or ADPKD. I didn't know anything about this disease until about 3 years ago. I have this fantastic mad scientist colleague, radiologist called Martin Prince. So Dr. Prince and I had been talking about various sort of collaborative projects over the years, and one day he came to me and said, look, we have this sort of interesting clinical cohort called ADPKD, and what we do is first of all, he told me about the disease, and he said it's a common disease, not super common, but common enough so that we have thousands of patients every year. And what happens in these patients is, they develop cysts in their kidneys. That's where the name comes from. These are benign cysts, but they proliferate and grow, and they crowd out the kidney parenchyma. They can spread to other organs like the liver. And you really want to keep an eye on the progression of the disease. So what you do is you often image these patients. You take MRIs, if they're lucky and have access to MRIs and they have insurance to pay for it. And so imaging is really the key tool to the management of these patients. Now, these patients often would come every year, maybe every couple of years, and get an MRI, and you're sort of looking for disease burden, you're quantifying progression, you're evaluating treatment, and screening for other things like aneurysms and infection. Okay, so an MRI study, which I'm showing to you on the left here, is, and this is a T1 weighted abdominal MRI that I'm flying from the front of the patient. This is an axial scan, so we're flying, sorry, this is the coronal plane. We're flying from the front to the back of the patient. I'll do that again, actually. Oops. If I can. Oh. Okay, and as you're flying through the abdomen, you might appreciate obviously all the internal organs, but you might notice all the cysts that this patient has in their kidneys and beyond. And so that's a T1 weighted MRI. And for those of you who are familiar with MRIs, there's various contrasts or various MR pulse sequences that you would typically obtain in a standard study. And in this case, you would have at least 4 or 5 different MRI contrasts. So you would have 4 or 5 of these types of images that a radiologist essentially would scroll through and try to interpret in the context of the disease of this patient and basically write up a report. And the report would, this is sort of a fake report on the right here that sort of conveys the gist of what the report looks like, but it would comment on the different organs and the different pathologies, and essentially wouldn't have many numbers in it, right? A typical radiology report is about 2 pages long and takes those millions of pixels and instills it into this narrative, typically unstructured narrative, that is commenting on the anatomy and the pathology as the radiologist interprets it. But you would rarely have any numbers. In the context of ADPKD, though, you would have a couple of numbers, and that's because things like the total kidney volume, the volume of the kidney, is a critical biomarker that's been well established for disease progression and clinical management. Okay, so how do you measure kidney volume in these pixels? So what you do is, traditionally, and this is by far still the most common approach, you would take 3 measurements, linear measurements. You find the sort of the biggest cross sections of the kidney, you take the depth and the width and the length, so you take those 3 measurements and approximate it as an ellipsoid using this volume formula. And you can imagine getting that would be relatively fast. You can do that in a matter of seconds, and radiologists have about 10 to 15 minutes to read these scans, so that's a good thing to do that quickly. But it's not going to be super, super accurate. In fact, we know that the error in there is going to be between 10 to 20% if you approximate your total kidney volume that way. So there's better ways of doing this, and the opposite extreme of this would be to go through every single slice of your MRI study where you see the kidneys and basically tediously draw the boundaries of the kidneys and get more precise measurements. And you can imagine that's not going to be fast. In fact, if you do that really accurately, depending on the skills and the expertise of the radiologist, it might take about 10 minutes per MR pulse sequence per kidney. So 20 minutes for the 2 kidneys, and then you have 4 or 5 sequences. That's about 100 minutes, right? That's an hour and a half plus. We're talking about just to get really precise measurements of the kidney volume. And that's not going to scale, and that's not going to be practical at all, okay? Now, that way, though, you can get really precise estimates of the kidney. And for those of you who are algorithmically inclined, who've been working on this, you immediately recognize the value of AI or an algorithm here to help with the segmentation task, right? Okay, but even with the tedious manual segmentations, you get an error that's often hovering around 5%. So that might not be great either. In fact, so time might not be just our only issue. We might also be worried about the precision of our measurements. In fact, to make this concrete, if you look at Mayo classification of this disease, which is one way to sort of discriminate patients if they're fast progressors or slow progressors or responding to treatment or required treatment or not. One way to do that is to look at the annual growth of the kidney volume. So every year, how much is the kidney volume growing? And this is sort of the table. If there's less than 1.5% a year, then they're kind of in the mild category. The 1A category is very slow. If it's greater than 6% a year, that's sort of very fast. Right, and between greater than 4.5% a year basically means that you probably want to try to intervene and manage this patient. Below that, you're kind of doing a watch and wait. So if you're in that sort of interventional category, the first line of treatment is what's called tolvaptan therapy, or it's a specific drug that works pretty well on these patients. When I say pretty well, on half the patients it slows down progression. On the other half, it doesn't work. And it costs in the US around $150,000 to $200,000 a year per patient. So it's a significant cost, and it comes with side effects, obviously, and it only works half the time. And you can imagine that the way we're going to try to figure out if the patient's responding to this treatment is to measure the kidney volume over time, over several months or years, and notice if there's a slowdown in the rate of progression of the kidney volume growth. And if this is the numbers we're dealing with, we need the precision that's around 1 or 2%. We can't 5% precision. Even that tedious manual contouring is not going to be sufficient to be able to tell whether a patient's responding to tolvaptan or not in a short period of time. In fact, the sort of standard of care today is based on those 3 linear measurements that I mentioned. You wait for a patient, you wait about 3 to 4 years to be able to confidently say if they're responding to a treatment or not. So that's 4 years of being on that drug, and half of the patients are actually not responding to the drug for those 4 years. So hopefully everybody in the room immediately notices that we can do this with AI. And that's what we did. 2.5 years ago, we started working on this project, and we basically said, hey, we have NN unit, we have all these different segmentation models. We can essentially go to town and devise our own architecture, whatever. We could work on the fanciest segmentation model, develop it, and develop like the most accurate model. I'll tell you a couple of things about that experiment, which I don't have data for, but you're gonna have to take my word for it, and we have some sort of paper results that we shared in our papers. One is, there was not a lot of meaningful difference between all the different architectural choices we made in terms of the quality of the segmentation results. And two, none of the models we were able to develop actually were perfect so that we can trust them 100% of the time for automatic segmentation. Basically, these models often made some errors, so that demanded some human review and correction. So what we ended up implementing is this human-centered kind of process that takes about 2 minutes for the technologists to review and edit the automatic segmentations. And what we achieved through this process, and by aggregating the volume measurements across all the different sequences that we're obtaining, we were able to get down to an error rate that's about 1.5%, which is really, really state of the art in this world. And it's transformative for the patients, because with that kind of error rate, we can actually tell if they're responding to treatment within a year or less than a year even for most of those patients. Now, this algorithm actually, or this pipeline, has been deployed clinically at Weill Cornell Medicine, where every ADPKD patient has an AI-assisted labeling done on their abdominal MRI studies. So I want to emphasize that our deployment was human-centered. We always have reviewers, and every single case is reviewed and edited and approved. And really, in this process, the model performance was not that big of a deal for us. Like, there was no meaningful difference between picking the best model versus the 7th best model in the things that we tried. The most important design element was how quickly the errors could be corrected. And importantly, and this is something I'm not going to talk much about, but I want to sort of flag here, is once the edits were done, capturing those edits, so the label corrections, and then feeding that back into the model training to be able to improve the future versions of that model. So those two elements actually were the most important, and from a selection standpoint, it really didn't matter which architecture we went with in the end. And we get these beautiful segmentation results that give us really precise measurement. This is an example patient where you saw on the x-axis you see the age of the patient, and the y-axis is the left kidney volume, and you sort of notice, you can observe the slowdown due to tolvaptan therapy. And you can also appreciate the sort of the variation of the different volume estimates from the different different orientations and the different MR pulse sequences that help us get a much more precise volume estimate by aggregating, doing some basic statistics on that. Okay, so the lessons from that first little tale I told you is that typical benchmarks focus on things like mean dice or inference time. Obviously you're using like a test set that is provided to you. But in the real world, when we try to deploy these types of models, what we notice is none of those things really matter that much. The most important thing that really mattered for us was the time to trustworthy result in the human-centered deployment setting, and like the robustness of the model, right? Like, we have various MRI scanners across our hospitals, whether the model worked well on a certain type of scanner or under certain type of protocol, and those were much more meaningful objectives that drove a lot of our design decisions. Okay, so now I'm going to switch gears and talk a little bit about a slightly different topic, but relevant as well. And that is, I threw up two quotes here from two ancient philosophers, Greek philosophers, and one's Heraclitus and the other one's Thucydides. You've probably heard of both, so maybe you don't know the names, but Heraclitus is the one who basically was obsessed with the notion of change. Everything's changing all the time. A person, when they took a bath in a river twice, it's not the same river. Those types of quotes you hear from him. And Thucydides was more of a historian, and he was like, it just repeats itself. History just repeats itself. And so there's these two extreme views of like how the world unfolds, and obviously both are, you know, correct to some extent, but incorrect also, right? Like, you know, some things change, some things are kind of repetitive, or some patterns repeat. And so I think that's all relevant for AI and machine learning. And so in the second part, I want to tell you quickly about this sort of other project where we tackled this notion of change sort of head on in a sense, because, you know, a lot of times when we deploy models in the real world in clinical workflows, say, if you monitor performance of these models, you'll notice that the performance will degrade over time. And the degradation of performance is really because the distribution of the data is going to be changing. Your scanner is going to be upgraded. The patient population is changing. You know, the protocols, the imaging protocols changing. And, you know, anytime there's a subtle change in the distribution, you know, your performance can really drop significantly. And so the world is changing. And if you don't have a system that can adapt to that change and learn from that change, I think you're bound to fail. And so in my mind, you know, the cardinal sin of machine learning, which in a way is the thing that allowed us to make progress, is the IID assumption. And so the question I have, or we've had been really obsessed with, is how do we move away from that IID assumption, the independent, identically distributed assumption, in a way that would allow us to adapt our models in the real world to new data. Now, the standard approach here is fine-tuning, okay? So I'd say 95+% of approaches out there in the world would basically take a fine-tuning style approach, whether it's self-supervised or supervised, and really the things that you focus on when you're fine-tuning, and this is stuff that we worked on as well, and we've got actually a paper right now on, is you know, you don't want to forget what you've learned in the past as you're fine-tuning. That might be a big objective. Obviously, the computational burden of it, like doing that in a sort of efficient way. And, you know, if you want to do this supervised, you know, how do you get the label data as you're going forward is also another challenge you might face. I'm not going to talk about these types of approaches. I'm going to talk about something very different. I'm going to bring up a sort of, this is a little bit of a detour, but I'm going to bring up a relevant concept called shortcut learning. And I'm sure many of you have heard of this concept. And it's really presented as this really big challenge to the field. And it started, you know, it was observed in computer vision, obviously extended later on to medical imaging applications, where essentially, you know, it was noticed that classifiers trained on data, on imaging data, learned to use some shortcuts to make those predictions. For example, in the case of like these chest CT scans, oh no, chest x-rays, I'm sorry, the model would use the chest tube in the scan to make a prediction about the disease. Obviously, that's not the disease, right? That's a treatment, and so it's a confound. It should not be relying on that to make the prediction. There was other papers that show like the orientation of the X-ray, like patients who had pneumonia were, you know, the images were taken in a certain orientation. Healthier patients were taken a different orientation, and the orientation of the X-ray was a giveaway. And so there was this whole sort of, you know, uproar about like the perils of shortcut learning and what to do about that. And what, you know, there's like a whole cottage industry on what do we do with shortcut learning? How do we train our models such that they're not relying on those cheat codes in our data? And really the goal of the game here is to suppress those unstable correlations, those correlations that we should not depend on, because when we deploy these models, the world is going to change, and maybe we're not going to have patients with the tube inserted into them. And so we want our model not to rely on that, but rely on the actual underlying pathology, for example. Now, our take on this is slightly different than what people have been focused on, which is, at the end of the day, I think, you know, rather than obsessing over whether the model is using some contextual cues or some cheat codes or whatever to make the prediction, the goal of the game is to get the prediction right. And the problem that we're dealing with is some of these correlations that the model is relying on are actually unstable. They might change over time. And if we don't adapt to those changes over time, then our model that we train will maybe its performance going to tank downstream as the distribution changes. So the problem in my mind is not confounding per se, because I'm not really interested in finding these associations to make any sort of gain any new insights or whatever. I want to just get the diagnosis right or the prediction right. And so it's really, the problem is how do I deal with these unstable associations? So a couple years ago, a couple of students of mine and I started working on this problem. And so we took a different approach where we really, if you like me and like really enjoy looking at directed graphs like these, we took Judea Pearl's causal framework and thought about sort of the data generation process, and in the context of medical imaging where we're trying to diagnose a disease, there's an underlying disease that let's call Y is the variable that describes the disease status, and X is the image that I acquire. So Y causes X, so X is a manifestation of Y, but X is also caused by lots of other things, right? Including the underlying anatomy, including the age of the patient, including the imaging device, the orientation of the image, the settings of the imaging device, so on and so forth. So there's all these auxiliary variables, that's all lump them up in A, that also cause X. Now, Y is unknown, it's shaded in this graph, it's latent. We're only given X, and we're going to make the assumption that we're given A as well, although that's a strong assumption and we relax that down the road. But given X and A, we're trying to predict what Y is, or estimate what Y is. Now, the relationship between Y and A could be variable, okay? So A could be causing Y. For example, A could be age of the patient, and age could be a risk factor for disease. They could be sort of independent. A could be the image acquisition, so prediction, for example, in the X-ray. Y could be just the disease. A could be, they could be like, they could be like a common cause, like socioeconomic status determines what kind of imaging is done to you, and also is a risk factor for disease many times, right? Unfortunately. And so there's all these possible ways A and Y could be related. And the key thing we made here, the key assumption we made is we don't care. That's the stuff that we're trying to kind of adapt and learn about as we deploy these models. What we're going to assume is that the relationship between the causal relationship from YA to X, those black arrows are constant though, they're universal. And the other stuff is the red arrows are the ones that are potentially going to change. Okay, if you're not very familiar with causal reasoning or the DAG framework that I presented, don't worry about it. The only way it matters is it's just how we're going to factorize our joint distribution. So the distribution that we're interested in is the posterior on Y, the label that I'm trying to predict, given X and A. I'm assuming A is given to me as well. Again, that's a strong assumption, but let's go with that for a second. And we've sort of factorized it in two terms, right? We have the posterior on X given Y and A, and then the posterior on Y given A. Now, the posterior on Y given A, the second term, I'm looking at this equation here, I'm sorry, which is in the bounding box there, is essentially the term that's unstable. It can change. I have a subscript S that means site-specific, but or whatever, it's local. The first term, Px given Ya, is universal. That doesn't change at all. The way the image is generated from X and A is just constant. And so the question then becomes is how do we, once we know this factorization, how do we take advantage of it to do machine learning that's going to be robust and adaptive? So the way we instantiate this is we create two sets of models. One is what we call the local models. These are site-dependent conditional models, which we call prevalence models or conditional prevalence models. Essentially what they are is they calculate the posterior on Y given A, these auxiliary variables. It's basically a conditional prevalence estimation. And if A is discrete, if A is just this few discrete values, then it's easy. You just do some counts. If A is polydimensional or real, then you can basically train a neural network on pairs of YAs. And the key here is you train separate neural networks or separate models at different sites or in different time periods for this piece. And this component, these local models can cheat. If at a given site, there's like a contextual cue that gives away the disease diagnosis, sure, let it learn it. And these models will basically learn all those unstable correlations, and because they're local, they'll be okay. Then there's the universal model. The universal model is quite interesting. It's an interesting object, really, because it's a posterior on X, the image given Y and A. And for those of you who have some probabilistic inclinations, you probably will freak out when you see a posterior on X. Like, how do I calculate that? And you might start thinking about generative models on images and whatnot. Thankfully, that's not something we need to deal with. And what we want is really, we want a model that can calculate a value for all possible values of y. These are our diagnostic labels, and say we're dealing with a binary situation where there's two possible labels. So there's only two possibilities that this model should calculate an output for a given XA pair. So an image is given because I observed the image. A is also observed, assumed to be observed, and I want just these two numbers that come out of this. Now these two numbers they don't represent probability. They don't sum up to 1. But, so I can't just do maximum likelihood or cross entropy on them. But I can combine the universal model with the local models to get a posterior distribution on y that I can do cross entropy loss on, or maximum likelihood on. And that's what we do. In the first stage of the model training, we train these local models that are site-specific and calculating these conditional prevalences. And then in the second stage, we train this big model, this universal model, on all our data. But as we're training for every site, we're using that site-specific conditional prevalence, which is usually a lightweight model, and doing just basic cross-entropy loss. Okay. Now, this is what we call this algorithm COPA, or conditional prevalence adjustment. And at deployment, now we've trained this universal model. We've got these local models that we've trained on our training data. When we deploy this in the real world, when we encounter a setting where we think things might have changed a little bit, what we need to do is we need to update our local model. And the local model then is a conditional prevalence model, and it requires us to have access to YA pairs, the ground truth labels and the auxiliary variables A's. Now that might be a strong assumption, might not be. In some settings it's actually not too bad. And so this is a kind of a weakness of COPA, that we need these YA pairs to sort of train this local model. But once we've trained it, we've sort of adapted to that. We combine it with our universal model, and we've got this phenomenal sort of global model now. Okay, we've applied it to a range of applications. Again, I'm not going to show you results, okay? But chest X-ray diagnosis was one of the motivations for us. So we've applied it there, and we have state-of-the-art results that I'm hoping that you're just going to trust me. But if you don't, you can check out the paper. And we've obviously shared the code and whatnot. The final remark I want to make about this is we've actually relaxed the assumption of the YA pairs being observed at this new site. It could be just, I've just got XA pairs, like the images and the auxiliary variables. It could also be that I don't have auxiliary variables, I don't observe them, or I have partial observations of them. So we have various sort of flavors of all of this that we've sort of talked about in some of our papers that I'm citing here. But feel free to email me if you have any questions about that stuff. Okay, so some quick lessons from that second sort of story that I told you is that we can really design effective adaptation methods by really thinking deeply about the data generation process and what's changing and what's kind of potentially universal or stable. And you know, it's a very different take on adaptation than what the majority of people are doing with fine-tuning. Because in fine-tuning, really, you're focused on just which weights of my model do I fine-tune? How do I make sure I'm not forgetting? How do I do this computation efficiently, data efficiently, whatnot? This is a very different take. It's really a sort of a model-based approach to adaptation. And interestingly, I think there's a sort of a general sort of lesson here that I'm hoping I can explore one, or we can explore one day, which is there's a way of like combining lightweight models with really heavy, large models for adaptation. The lightweight models would basically be your adaptation tools. Okay, so I'm going to end on where I think radiology is going, because I started with like Jeff Hinton's prediction about how deep learning is just going to kill radiology. I don't think that's happening, obviously, for many reasons, because the benchmark results don't really translate into the real world. There's all this work that we need to do in the real world for radiology to be sort of impacted. I think what's clear to me is, we're getting better scans thanks to AI. Like, we're getting compressed sensing and better reconstruction models are giving us higher quality scans, higher resolution scans, scans that we can acquire with lower risk, without contrast, say, or with lower dose X-ray. It's also allowing us to extract these quantitative things like measurements out of our scans and enhance our radiology reporting. So as I said, radiology reporting today, by and large, is really very narrative-based. We can actually append that narrative report with a table of measurements that we can extract from the images that are quantitative and reliable, and hopefully give us like strong biomarkers to understand disease progression and treatment response and whatnot. And there's all these interesting workflows that I think are coming up as potential problems that we can all work on, which is like triaging. How do we decide which patients need to be seen by, which patient's data needs to be seen by a radiologist first? Because if you look at the workflow of radiologists, as I said, they're overburdened today, and sometimes it takes days or at least a couple days before a radiologist can get to a scan, and you really want to make sure that patients who are kind of in an emergent setting get their reads as soon as possible. Another paradigm that I think is becoming interesting, it's sort of a convergence of multiple threads in society these days, is medicine and healthcare to this day is really reactive, right? We sort of diagnose a patient based on symptoms and tests, and then respond to those to that diagnosis by treating that patient and follow up with that patient to see they're doing okay. But it's clear, at least, there's a trend towards wellness and just health span and longevity and prevention, right? So it's there's a growing demand for these images that we're acquiring, right? In a clinical setting, often for diagnostic purposes, contain much more a lot of information about just the wellness of the patient, right? A chest CT scan is not just about your lungs; it contains information about your spine health. A breast imaging scan might actually contain information about your cardiovascular disease risk. An abdominal scan might have a signal in there about your metabolic health, not just the cysts in the kidneys. So there's a lot of value in these scans that potentially can be extracted thanks to AI, right? Radiologists don't have the time or expertise to really look for these things, but AI is going to allow us to opportunistically actually scour these pixels for these types of other indications or other wellness metrics that will allow us for prevention to do prevention or detection better. There's a lot of interesting open questions that I want to quickly highlight here, which are, how do we, when you think about an AI model, what in the workflow, what does that output mean, right? How is it going to be useful for the radiologist or the downstream care provider or even the patient? How does it become part of a medical record? There's legal questions there, actually, that's important. And what does the future of radiology reporting look like? There's obviously an increasing, capabilities of report generation, for instance, by these, large language models. Is that going to be like are we going to use that as a drafting scheme, and then, the report is going to be then fine-tuned by radiologists, or is there going to be another way of implementing that? Again, what do we do with these incidental findings that come out of opportunity screening? Say you got a breast MRI for breast cancer screening, but the AI model said that you have cardiovascular disease or a very high risk for cardiovascular disease. How do we act on that information, right? Like, what is the ethically right way to do that? That's also, responsible, right, in terms of resources as well. Okay, and one final word I want to make is, in this world where we're deploying AI models, I really think that 5-10 years from now, we're going to have hundreds of these models in these systems that are interacting with each other in the real world, in clinical workflows. And I do think that that demands a very different way of thinking about evaluation and validation and picking and choosing the right model. Today, medicine is dominated by the randomized control trial, right? When we're thinking about a medical device or a drug, we conduct a trial once and decide that it works, and then we recommend everyone that uses that drug. Obviously, that's not going to work in the world of AI, right? Where these models are just coming out daily, weekly, and they're interacting with each other. It's really impossible to really do an isolated trial of the quality of the model. And so we've been thinking a lot about how do we evaluate these medical AI models in clinical deployment scenarios. All right, I'm going to end here, but there's 2 take-home messages. Real-world impact is going to be multifactorial. Don't just hyperfixate on die-scores. And I truly think that model performance, the way we measure it in benchmarks, is not the most important thing. As long as it's good enough, then there are many other factors to think about when you're deploying these models. Thank you.
Okay, great. So thanks for the inspiring and wonderful talk. So any questions from the audience? So there's a microphone there. Yeah, please.
Hey, very great talk. Thank you a lot. So you made a really good point of how we cannot fully trust fully automated systems, and there's like a shift towards this human AI interaction. Can you maybe give some more thoughts on how to balance this, that you have maybe also new types of jobs where people are doing data engineering in the clinics, or this manual interaction? Does it really have to be a radiologist who does it?
No, that's a fantastic point. In fact, in our deployment, it's not a radiologist. We have dedicated technologists who we train, and that's sort of a different skill set if you think about it. They have to understand anatomy, and they have to understand how to interpret the image and the output of the AI model. But it's sort of often a pretty repetitive task, and once you've trained a person, they can do it well. And I think it's definitely a different skill set and a different job than your typical radiologist. And radiologists are expensive, and you don't want to be using them for this kind of task either. So, but yeah, that's a great point. I mean, this is a great example of like AI creates a new sort of job area, right? Where it's reviewing and editing and improving the quality of the model's outputs.
And then on the other end, also to prepare the data differently, so kind of look for the cases that are relevant for the AI model to be trained on.
Oh yeah, yeah. We haven't done much work on that, I must say, but yes, the curation of the data, that might benefit from some human expert interaction. I haven't thought much about that, to be honest. But yeah, I mean, a theme that sort of I'm hoping we can really emphasize more in our research is the computational efficiency, right? I feel like in the world we are with the sort of how AI is progressing, there's sort of this, compute. Obviously, we're all restricted with computational resources, like we don't all have infinite GPUs or whatnot. But we sort of our attitude is like we want to get our hands on the biggest computers as much as possible, as the biggest possible, right? But I think it's clear that that's not very efficient and probably not responsible to do. And so that translates to training, right? Do we want to train on all our data, or do we want to pick and choose the right data to train on? And I think that's an interesting research question that we haven't done much work on. Yeah.
Thank you.
Thank you.
Hi, thanks for the great talk. If I understood correctly, the manual segmentation was 5% they had an error, but that's probably where the biomarker was found. So I was wondering, and your model was 1.5% error, but then you still had it manually perfected. And how did you choose that? Like, how do you choose that you still need some manual perfection, or when do you say the model's good enough?
You're actually asking a very nuanced question that I wasn't hoping to get into, but the question there is, what's the gold standard? Like, how do I measure my error? Right? Like, I have a bunch of I have like 5 independent manual contours actually for these cases. And I have the models output. I have the revised models output by 5 different people as well. The models output, vanilla, automatic output, was not at 1.5. I actually did not, I sort of skimmed over that, but it's like more than between 2 and 3%. So 1.5 was the reviewed and edited. So the gold standard we're always comparing against is like the aggregate of 5 annotators. So it's a consensus that obviously you can't get at scale. But assuming that aggregate is your gold standard, you can get to within 1.5 of that with the review and edit of an automatic by one reviewer.
But then, let's say the model does 2 to 3%.
Yeah.
Would that still not be a viable biomarker that would maybe
It could
cost
be.
a lot less?
I think it depends on. It definitely could be, right? I mean, we're kind of lucky enough to be in a setting where we have the resources to offer this to our patients, right? One thing I didn't mention. I mean, if you go on, we actually made all these models available on traceorg.com. Easy to remember, traceorg.com. And anyone in the world can upload their data. If there's any PHI, sensitive information in the headers of the DICOM files, it gets stripped away, so we get anonymized data. And we process it and send the segmentations and the report back to you. It's easy to download. It's fully automatic, and actually patients and doctors across the world are using it as is without any corrections. I mean, if you can review and edit, I think it's much better. Without corrections, I think, I don't have hard numbers on this, but I would assume you would have to wait at least 2 or 3 years to be sure that tolvaptan's working or not on a patient. In our case, we can actually do nowadays within 6 months, which, if you can do it, that's amazing. But again, it's resource intensive, yeah.
Yeah, thanks.
Thank you.
Okay, yeah, we still have some time.
Sylvain has a question.
Yeah, one more question.
Hi, Mark. Thank you for the talk. This is not a medical imaging question or a deep learning question, but a regulatory question. So regulatory bodies don't really like things that adapt, right? You seal the box, it's approved by the FDA, and then you can deploy it. Do you know or see any shift in how these things are, these bodies are thinking, so that we'll be able to do that?
Yeah, absolutely. Yeah, traditionally, you know, when FDA or similar entities think about regulating these models, they often think about the phase where you sort of validate the quality of the model and it's frozen, like nothing changes, right? But we all know that that model's not going to perform the way it did on validation data. That posture is changing, at least with the FDA. So FDA is definitely exploring ways of allowing technologists to update their models in a prescribed manner. So you have a protocol where you say you're going to update the model, but then there's a way to objectively quantify performance, and there's like a cutoff. If the performance is above a threshold, the new version of the model is good to go, and you describe everything in great detail, how that validation happens and how the update happens. So that's, I forget, there's an acronym for that. It's like a pre-registration scheme. And they're now allowing that. So you can get approval for your model that you're going to update in the future with that, as long as you've prescribed everything that the way you're going to do the update and the validation in the future. It's a little narrower than you would hope for, but you know, it's a step in the right direction. And I think there's no doubt in my mind that FDA is going to be open to that, and I think that's going to, everybody else is going to follow FDA's guidance on that. The other piece of that, though, is one thing that people don't often realize is, you know, FDA only care about what your label says when you're selling a model, right? So, you know, if you claim that you can diagnose a disease with this model on a CT scan, for example, and you're going to make that claim, and you're going to have insurance payers or, you know, payers pay for that model to be used in a diagnostic setting, FDA cares about that claim. Now, if your model is used in a human-in-the-loop kind of paradigm where the model is basically providing, you know, efficiency gains, essentially, and the human's always interrogating the result and making the final decision, there's a very different regulatory landscape there, right? It's a much more relaxed landscape. The model can be updated, actually, there much easily. So I'm, you know, in radiology, I am much more in favor of those human-in-the-loop type deployment scenarios, obviously with the caveat being that you have to have technologists or trained experts in the loop that are going to be expensive. But as long as you can do that, I think that's a better strategy, at least at this phase of where we are with the technology.
Okay, great. So thanks for the question and also giving the time. So we will be ending this session. So let's thanks again Professor Mercier-Benchou for his wonderful talk. Yeah, and then we will have a poster session, and also we'll have like one message from our general chair about gala dinner tonight. Amazing gala dinner.
So, okay, I hope everyone enjoyed the technical session, right? But the conference is not just about technical session. I think I want to emphasize a little bit about tonight. Will be a very different gala dinner experience, and I live in old time. You know, 26.5 years ago, I had a gala dinner at the Grand Hotel. Like that was January 2000, year 2000. That was 26.5 years ago, right? That was my best and the first and the best gala dinner ever, even until now, right? So let's see, like tonight, like we're trying like to let you memorize something which does not really happen in the nowadays. You know, nowadays you go to Mikai, CUPR, the conference is huge, you get a sandwich, right? And if you notice that, and one of the general chair told me yesterday, you know, the wrap yesterday, I did not try it today, was from a Michelin star, like a local restaurant. I'm not sure if you can tell the difference, but anyway, so tonight, we'll be at the Grand Hotel. Grand Hotel that's on the, you can see that the red building like across the road on the mountain. We'll have should be very good like a gala dinner. It's like you consider it's like a $70-80 US dollar per person budget. We should get you very good food and make sure you'll be there. And we hope that experience you can memorize for years to come. You can always say, hey, I go to see this food, it's not comparable or something. I hope you enjoy the conference. Yeah. Oh, enjoy Taiwan. Yeah. Thank you.
Hello? Oh. Hello, everyone, for coming to this afternoon session on segmentation detection and structural detection in medical imaging. I'm Yihao Liu from the Vanderbilt University, and our course co-chaired by.
This is Ulash Baj from Northwestern.
So we will have 4 oral presentation followed by 4 spotlight. And do we have the presenter for the first? Yeah, so the first presentation is titled PAGT, Hierarchical Multi-Teacher Knowledge Distillation for Comprehensive Tumor Microenvironment Segmentation. Let's welcome the presenter.
Okay. Good afternoon. My name is Daisuke Komura from the University of Tokyo. Today I will present PAGT, method for comprehensive tumor microenvironment segmentation from hematocxylin and eosin images. So hematocxylin and eosin slides are collected routinely in clinical practice, and it contains a lot of information about cancer. So for example, there are tumor tissues and stromal tissues and various immune cells and vascular cells and so on. And the distribution of such tissues and cells are correlated with clinical outcomes such as therapy response. So it is very important to identify such tissues and cells accurately from H&E images. So, but it is still challenging. So the aim of this study is to develop an accurate and fast segmentation model from H&E images using deep neural network. There are 2 major limitations in this field. The first limitation is a lack of accurate and sufficient training data. So to develop an accurate segmentation model, we need many annotations of various tissues and cells, but it takes a very long time for pathologists. And additionally, there are some hard to label cells. For example, in the left figures, these plasma cells on the lymphocytes have a typical morphology, so it is very easy to label. However, these cells in the right figures have a typical morphology, so it is very hard to label even for expert pathologists. The second limitation is inference time. So if it takes long time to process whole slide images, large cohort analysis is impossible. So for example, if it takes 60 minutes per slide and there are 10,000 slides, it takes 1 year. To solve this problem, we previously developed SegPath dataset to improve the quantity and quality of the annotations. SegPath utilizes restaining annotation, so instead of manual annotation. In SegPath data generation, we first stained the slide with H&E, then destain the slide and restain with immunohistochemistry. So marker signals provide objective cell and tissue labels. So for example, alpha SMA antibody can identify smooth muscles, and the CD45 antibody can identify leukocytes. So by doing so, SegPath can generate accurate masks at the large scale for training segmentation models. But there's a limitation of this approach. Because the marker signals are obtained from different slides, SegPath requires separate models for different tissue and cell types. So multi-class TMA segmentation requires repeated inference, which takes very long time. So to solve this problem, we developed PAGT, which utilizes hierarchical multi-teacher knowledge distillation. In the generation of PAGT dataset, the pseudo labels are generated from a series of teacher models. In this model, the point is cell types are biologically hierarchical, not flat. So for example, leukocytes have several immune cell subtypes, such as lymphocytes, plasma cells, myeloids, and the neutrophils and the eosinophils. So CD45-based SegPass teacher can detect leukocytes, and then subtype teachers define immune cell classes. Such hierarchy-aware aggregation resolves course to fine teacher predictions. We also include additional teachers which cover fibroblasts and mitotic figures which are not included in the SegPass dataset. Additionally, we created two variants of Paget. Paget S is a first semantic segmentation model, and Paget H is a panoptic cell segmentation model by adding the nucleus segmentation result from HOVANET. So I will show you the aggregation algorithm for teacher label generation. The first step is a spatial initialization. HOVANET is applied to extract nucleus instances, and the O2 thresholding on images identifies background pixels. In step 2, for each pixel, we assign a tissue label based on SegPass tissue model logits. The tissue model includes epithelium, stroma, smooth muscle, and blood. In step 3, hierarchical nucleus classification is applied. So classification was performed hierarchically at the pixel level, where final level teacher predictions overrode cursor labels when positive. For each detected nucleus, the final label was assigned by majority voting over non-background pixels, with leukocyte nuclei further refined to the most frequent immune subtype when present, like this. In step 4, to complete the label space, unclassified nuclei in epithelial region are labeled as epithelial cells, and HOVANET connective nuclei not identified as the other cells were assigned as fibroblast. Finally, mitotic figures are detected by the other model trained on MIDL++ dataset or added to the final nucleus labels. So we conducted ablation study of hierarchical aggregation. As shown in this table, hierarchy-aware aggregation improves dice scores for fine-grained immune cell classification, such as neutrophils, eosinophils, and lymphocytes. So for hierarchy is especially beneficial for deeper level immune subtypes. Next, we compare the segmentation performance of Paget with teacher models and HOVANET, HDYORO, and servers. From this result, Paget S and Paget H outperform or are comparable to other segmentation models in most tissue and cell types. Interestingly, both Paget S and Paget H outperformed their teacher models in almost all categories. I think this is because the training of a Paget model is a kind of a noisy student, so we apply the heavy data augmentation, which makes the model robust to the domain difference. Finally, we evaluated the computational efficiency of Paget S and Paget H. So as shown in this table, Paget S is very fast. So Paget S can it takes only 1 minute per small-sized whole slide image, which is more than 300 times faster than teacher models. In contrast, Paget H takes 2 hours per whole slide image, but it can detect precise nuclear boundaries. So if you need speed, if you need large-scale analysis, Paget S should be used. And if you need precise nuclear boundaries, Paget H should be used. So to summarize, Paget is a hierarchy-aware multi-teacher distillation framework for comprehensive TMA segmentation. It integrates heterogeneous teacher models into biologically consistent pseudo labels. And it uses cell-level hierarchy to resolve conflicts between coarse and fine-grained predictions. And it trains a single first Paget S model for scalable whole slide image level semantic segmentation and achieves a strong generalization across external dataset while segmenting 13 TME components. That's it. Thank you.
Any questions from the audience? In that case, I have a question. So in this hierarchical process, have you investigated whether the improvement mainly coming from the hierarchical or it's because it's trained jointly for from all the teachers?
The improvement is from it's only for immune cell subtypes. Sorry, I don't follow your question, so please, could you repeat that again?
Oh, so I was wondering whether the improvements you observed mainly coming from this hierarchical structure that you deployed, or it's because it's learning from all the teachers?
Yeah, so but so you so sorry, I don't understand your question exactly. So that
is the question clear?
Yeah, not really. So we have all the models and the hierarchical aggregation as Python, and so the question is.
So I guess my question is, because you have this hierarchical process, it's your lower step can refine. It's segmenting in a more confined space, right?
Yeah.
On the other hand, you also use a really large data set that's learning from many teachers.
Yeah.
So if without this hierarchical process, like if you're purely learning from this large number of teachers, can you also achieve very good performance, or you think it's mainly contributed from the hierarchical process?
But in this experiment, the models are all the same. So on the hierarchical aggregation apparently improves the performance. So.
Okay, thank you. Yeah, let's thank the speaker again.
So I would like to invite our second speaker, Ziyao Gao, from the Chinese University of Hong Kong. He's going to present temporal memory enhancement for semantic segmentation in surgical video.
Hello everyone, my name is Ziyao Gao. Thank you for attending. I will be presenting the paper on behalf of our research team from the Chinese University of Hong Kong. The presentation today will be divided into two parts. I will first introduce the background of the problem, and then I will detail the methodology. And segmenting critical anatomic structures in surgical videos is essential for intraoperative guidance systems and preventing complications. And in this work, we mainly focus on two surgical procedures, the ESD and LC. As shown in the pictures, we can find that these datasets suffer from heavy class imbalance, and some critical structures like blood muscles and cystic duct are very easily overlooked. And because of motion and light changes, and the appearance of the tissues varies drastically during time. So we need accurate segmentation of these tissues requires sophisticated temporal memory, temporal context integration. And traditional video segmentation methods often relies on a fixed range local memory to incorporate temporal features from past frames. But this strategy could introduce two challenges in surgical domain. The first is that the surgeons often operate at a highly variable motion paces. And a static memory strategy could be filled up with redundant frames during the slow motion, and it could miss critical structure in the fast motion. And the second challenge is that the surgical procedures often follow a structured workflow with long-term context. And the previous local memory strategy could not capture such long-term context shared by frames within each distinct phases. So we want to propose a temporary memory enhancement method to deal with both challenges for surgical video segmentation. Our methods mainly consist of a dynamic local memory selection module using a determinant point process. It filters out redundant frames and selects the best reference features for segmentation. And it also consists of the global memory that models phase context via a conditional variational autoencoder. Now I will dive into the details of the local memory. Our objective here is to find a subset of memories that maximize two properties. The first is the diversity. It ensures that we do not store redundant frames. During the slow motion phases. And the second is the relevance. It ensures that we filter out irrelevant frames, such as frames corrupted by motion blur or artifacts. And then we formulate this problem by first deriving a matrix that describes the similarity between all pass frames and a relevance matrix that indicates the relevance of all pass frames to the current frame. So we can use these two metrics to find the optimal subset by maximizing the determinant of the combined matrices. However, finding the exact optimal subset is compute intensive, which is impossible for the real-time surgical video segmentation. So we employ an efficient subset selection strategy named as orthogonal matching pursuit. This algorithm maximizes and selects the subset one item at a time, and it always maximizes the determinant gain. And this method reduces the time complexity drastically from the exhaustive methods. Here we use a toy example to show the algorithm. We can see in the figure that it first selects the feature that is close to the current feature, and then it gradually includes other features that are distant to each other. So in this way, it selects a subset that is relevant and diverse. Then I will move to the global memory. The objective of the global memory is to capture the common visual and semantic pattern shared by frames within each distinct phase. For example, in mucosal incision, there will be no muscle tissues in this phase. And this prior information is very important to avoid false positive predictions in the segmentation. So we want to model this prior information as a latent phase context using the mixture of Gaussian distribution. And each cluster in the mixture distribution accounts for a distinct phases in the surgical procedure. And to formulate this problem, we use a probabilistic graphical model to represent the segmentation process, where the segmentation mask is dependent on both the image and the latent phase context. So during training, our aim is to find the posterior that effectively learns the phase context based on both the image and the segmentation mask. And our method uses variational inference to find the posterior. And our training objective is to maximize the evidence lower bound using two loss terms. The first loss is a cross-entropy loss from the mask decoder. And the second loss is the KR divergence loss. It forces the prior distribution to align with the posterior, which encodes the segmentation patterns. And then we specify these prior and the posterior with the categorical and normal distributions and with learnable parameters. In practice, we estimate these parameters using the posterior and the prior network. So during inference, we can sample the phase context using the parameters estimated by the prior network to enhance the mask decoder. Okay, now I have covered all the methodology. I will then walk through the experiment results, discussion, and conclusion. We have compared our method on two public datasets, the LC and ESD, with CN-based and SAM2-based methods. You can find in the table that our methods achieves the state-of-the-art performance across all segmentation metrics. And we also maintain a highly competitive processing speed, which adds little efficient cost compared to baselines. And the radar charts below also highlight that our method outperforms other methods on these critical but small structures, such as the cystic duct, artery, and the blood vessels. These are very important for building the surgical guidance system. And these visual results also confirm that our quantitative findings, compared with foundational models like SAM2 and other surgical-specific models, our methods achieve more coherent predictions. And it can be seen from the figure that the segmentation of the blood cell is more accurate by our methods. And we have also conducted an extensive ablation study to validate our module design. According to the table, removing either the relevance or diversity from the DPP selection module will cause a significant performance drop. And we can also find that introducing the clustered phase context is also important. And on the figures below, we can find that the DPP selection is more important as the memory size grows larger. And we also find that our performance peaks when the number of clusters aligns with the true surgical phases. This indicates that our global memory actually finds the phase context. Okay, in conclusion, we propose a temporal memory enhancement strategy to capture the complex dynamics in surgical video segmentation. Our contribution includes a dynamic local memory management system, which uses the DPP selection strategy. And it also includes a phase context-aware global memory using conditional variational autoencoder with a mixture of Gaussian prior. Together, this strategy improves segmentation performance with little computational overhead. And but we also acknowledge that our models have some limitations. For the unreliable, we could generate unreliable relevance scores for those obscure frames in the local selection strategy. So to address this, future work could avoid direct prediction based on these frames. And our method uses a fixed number of clusters, which could limit its generation to other workflows. Okay, that's all for my presentation. Thanks for listening.
Presentation is open for question, please.
Yeah, thank you for the presentation. Very nice work. You have this efficient selection mechanism, right?
Yeah.
Did you also compare the scores, or maybe I missed that? Did you also compare it to the exhaustive selection, or is this something that you did not compare?
You mean I have compared with the exhaustive method, the performance?
Yeah, indeed.
Yeah. I actually have compared. The performance loss is very, very marginal. So we do not provide those results on the paper. Actually, it is theoretical grounded. It can be proved that the performance loss is within 10%.
Okay.
Yeah.
Okay, all right. And one more question. It's a temporal modeling strategy, right? Did you also explore maybe temporal metrics beyond the die score or the other scores?
Okay, you mean the temporal consistency?
Yeah, indeed.
Yeah. I think our main contribution is not to improve the temporal consistency. We just want to adapt the memory to capture the specific challenges, to avoid the specific challenges in the surgical things. So we do not provide any specialized strategy for improving temporal consistency. So we do not report in our paper. Yeah.
Yeah, right. So you're more focusing on getting basically a better segmentation rather than a consistent one.
Okay.
Right. Okay. Thank you.
Thank you.
Next question.
Thank you for your presentation. I have just first a basic question. So you were talking about the challenges regarding motion in surgical scenes. Did you mean more motion in regarding the tissue itself, or also the camera movement, or the entire scene moving?
Yeah, actually, I mean the entire scene moving, because this is caused by the surgeons. When they operate, they will move the camera very fastly or slowly. So actually, this is caused by the camera, I think. Yeah.
So your methods would make the temporal memory more robust with regards to camera movement also?
Yeah, actually we improve this by modifying the local memory. Yeah, we select very more useful features for enhancing the current feature segmentation. Yeah.
Okay, thank you.
Thank you.
Go ahead.
Okay, quick question. So you mentioned the two challenges. The first one is the class imbalance, and the second one is that different phrase. Maybe you show different motion, and then I'm wondering how this can be linked to your methodology, like especially the memory part.
Okay. Actually, we have mentioned that the imbalance and the temporal the motion varies. So that's why we want to design a specialized memory instead of using the conventional 7-2 style memory for natural scenes. Because the local memory in conventional video segmentation models could not capture such long-term context, so they don't know the face context, and they could miss the critical structures in fast-moving things and store more redundant frames in the slow-moving things. This will decrease segmentation and the performance of memory module. Yeah.
Okay, thank you. Very quick one. So, I'm wondering whether this kind of like face label has been explicitly embedded into the model designing or training.
Oh, actually, no. We don't think explicitly incorporate the face label is not a very wise strategy, because actually we want the model to find the common pattern dependent on the segmentation, because we are aimed at segmentation instead of workflow recognition. So even if we identify the workflow label manually, this may not coherent with the segmentation pattern. So I think this will be undermines the performance. Yeah.
Thank you so much. Thank you.
Thank you.
So let's thank the speaker.
For the next paper, we have beyond scalar losses, calibrating segmentation models with gradient vector field surgery. Let's welcome the speaker.
Hello, thank you. Today I will present our work beyond scalar losses, calibrating segmentation models via gradient vector field surgery. And what this project is actually all about is finding an optimization scheme that works in optimizing region overlaps metric like dice, Tversky, IOU, and other losses do it, but also provides calibrated outputs at the pixel level and therefore overcomes the overconfidence problem that is inherent to these losses. And what this is interesting for, we heard today a few examples at the keynote. For example, for clinical verification, if we have lesions that might be there or might not be there, where overconfident results would just go to 0 or to 1. And also for having error estimates on, for example, volumetric metrics, where you can see on the right side the yellow part in the boundary, where it's not sure if it still belongs to the volume or not, and we can propagate these errors in the analysis. So As you know, losses like the cross-entropy loss are strictly proper scoring rules, and they will provide calibrated outputs. And if we look at the partial derivatives at the level of the logit or of the probabilities, this gets quite clear. If we have samples that share the same underlying representation in the model, but have conflicting ground truth information, then the gradient will cancel at a specific probability. And for the case of the cross-entropy loss, this happens exactly at the 50% probability, which is the calibrated output, because the empirical accuracy matches the probability where the gradients, where the partial derivatives also match. The problem is for region-based losses that are actually just adaptively weighted mean absolute errors, and the adaptive weighting comes from the global state of the segmentation quality, is that this cancellation does not really happen because the magnitude of the partials at the level of the probability is actually error agnostic. And at the level of the logits, we only see these cancellations at extreme probabilities or zero or 1, and what will happen in practice for dice loss, where usually the foreground will be weighted higher than the background, is that you will just push the matched probability for a specific representation to an extreme. So in this case, it would be 100% for both labels. And looking at different fractions of ground truth labels sharing the same representation and plotting this equilibrium coordinate, we can create actually these equilibrium diagrams that will show us what we expect from the calibration behavior of a loss. And you see that cross-entropy has the perfect behavior that we want from a calibrated output. But what we see for dice is this completely degenerate behavior where we will only see cancellations at the extreme probabilities of 0 or 1. So noticing this problem, the question for us was, how can we come up with an optimization scheme that has both these advantages of the adaptive weighting that the dice loss has, and also the calibration properties that we get from losses that are strictly proper scoring rules like the cross-entropy loss. And our very primitive idea was to just come up, because we already analyzed this now at the level of the logits, with a vector field at the level of the logit that combines the merits of these two desired features. And one is the adaptive weighting of foreground and background, that depends on the current state of the segmentation. We get this by taking the partial of the dice loss with respect to the probability. And then we did really a just super simple multiplicative combination of this with the error dependence that we have in the cross-entropy loss, the linear error dependence at the level of the logits of the cross-entropy loss. And what we end up with is this vector field that can actually be used for optimization, where now the signal from every single pixel depends on the global state from the dice part and also on the error of the single pixel from the cross-entropy part. So obviously the next step is just to formalize this into a loss. But here a problem occurs because the dependence of the local state, so the error and also the global state, how well the segmentation is at a specific moment, it actually introduces curl into the vector field, which results in this specific vector field not being a conservative vector field. It has curl. You see on the right side the extreme version of a curl field, which obviously is extremely bad for optimization because you would just orbit around your optimum and not find it. But for our specific case, we noticed that the curl is extremely small, and already non-zero curl is enough to not find a loss function. There is no corresponding loss function in this case, but it does not mean that you cannot do optimization. And this is exactly what we do. We do not do gradient descent, but we define a vector field for optimization. At this point, we noticed that there is one more really crucial aspect of the dice loss that is essential for medical image segmentation, and this is robustness to label noise. Because the MAE, since dice loss is just an adaptively weighted MAE, and MAE is in the signal agnostic to how strong the error is, And we also have the sigmoid activation. Is what would happen for the dice loss is that if you have an extremely confidently wrong pixel, you do not propagate a strong loss signal. And this just on the left side, you can see how the derivative of the sigmoid activation function looks like, and you see that at probabilities of 0 and 1, just the partials are more or less 0. So what we came up with is this term that you see on the right side, which is just a symmetric dampening around the probability of 0.5 that can be tuned with this exponential factor n here, that actually is a scaling of how far we want a strong loss signal. For example, we can get strong signals of probabilities from 0.1 to 0.9, and at one point when the model is extremely confident that something actually belongs to another class, we will have the decreased influence of the gradient. Interestingly, this term, if we ignore the part in the middle that is the partial derivative of the dice loss, is interpolating between mean squared error and cross entropy loss, which are both strictly proper scoring rules. And with this, it's actually also a strictly proper scoring rule. So with this vector field defined, we found we can actually do optimization now that yields results that provide high dice scores, as we cannot obtain them usually from using cross entropy loss. But at the same time, we get much better calibration properties here measured in terms of the expected calibration error and also the negative log likelihood. And it can be adapted to any region-based loss. This is not specific to the dice loss. You see it here in the results table. For dice loss, Tversky loss, it will also work for IOU, and also for compound losses, such as the combo loss, the cross-entropy loss, plus the dice loss. So, to summarize what we did, is we came up with a solution for the pathological overconfidence that is inherent to all the region-based losses by introducing a vector field iteration as optimization scheme instead of gradient descent, and by introducing dampening terms that interpolate between MSE loss and cross-entropy loss, we gain the label noise robustness that is essential for working with medical imaging segmentation. And this proves to maintain the high dice scores that we get from region-based losses while drastically improving calibration metrics. With this, I'm at the end of the presentation, but I want to thank all of my co-workers, Alex, Moritz, Johannes, Daniel, for making this work possible. It was not me alone. Thank you. I'm happy to answer all your questions later at the poster and also happy to take them right now.
If there's no question from the audience, so I want to ask, can you comment on how difficult is the implementation, and do you recommend this adjustment for all applications?
The implementation is super simple. It's just the way we solved it was just to do a custom backward pass in the activation function. And in this custom function is 5 lines, so the change is actually just 1 line. Regarding using it, I mean, what we could really see was that negative log likelihood and calibration behavior gets much better. So if this is important for your task, then you should definitely try it, I would recommend. Regarding applicability to all different networks and data sets, the severeness of the curl, I think it also depends. It's not, it's specific to data set and architecture. So you need to try, but for us, we tried on 2 data sets for 3D metastasis segmentation and 2D data sets for vessel segmentation and breast mass segmentation, and there it worked really well. So I would be happy if you try and see if it works.
Let's, oh, yeah.
All right. Sorry. Maybe I shouldn't have done this, but The curl being non-zero, right? So you're not optimizing any loss function, but in many practical instances, we really want to monitor validation loss, like for early stopping or hyperparameter fine-tuning or whatever. What do you do then? I don't.
This is super simple because we can still just track the dice loss and also the negative log likelihood loss. We just follow the vector field and also track the dice loss, and you will see the same loss curves for the dice loss more or less.
And is that a way to diagnose the curl issue sometimes? Like if it's not working for you, this vector field for an optimization objective, does that?
I think since we also have a visualization at the poster of the curl. I mean, we can only see it specifically at the level of the logic. It's still general to only the data set and not to the architecture. At the level of the architecture, you would probably need to do a theoretical analysis for every single architecture. But there it's really small, and I think the only thing that would happen from this curl would be that this optimization would maybe get slower. But I don't think that you would never reach an optimum.
Let's thank the presenter again.
So I would like to invite our fourth speaker, Chi-Wei Chang from Emory University. So he's gonna talk about a deep learning-enabled digital twin framework for fast online adaptive proton therapy. This is a validation study in a prostate SBRT clinical application.
Thank you, Chair, for the introduction. Hello, everyone. My name is Chi-Wei Chen. I'm from Emory University. I would like to present the work, how we combine the medical imaging, deep learning, and the digital twin strategy to support the radiotherapy. This is the joint work between Emory and the University of Chicago. We all from radiation oncology department, so my work will directly relevant to the clinical application. Before we start talking about our proposed framework, I would like to spend a little time to introduce the workflow for radiotherapy. So for the radiotherapy, if we look at the lower chart, starting from the very beginning, when we bring the patient into the hospital, we need to acquire the CT simulation to get the anatomy of the patient. And then from there, we will contour our target, which is the tumor location, based on the multifunctional imaging that could be from MRI or PET, and then we contour the tumor on the CT imaging. Then we will have a dosimetry to contour all the organ at risk to use the information to support our treatment planning. And then the planning-wise, we use the inverse optimization to guide how the radio treatment machine to deliver the radiation to our target while we can maximally spare the healthy tissue. During the delivery, one important step is we need to set up the patient to reproduce the CT scene position. In that way, we have a confidence in our treatment plan. And nowadays, all the treatment machine, which is shown at the right corner, lower right corner picture, this is a proton therapy machine. At the center, this is the treatment nozzle. It will deliver the proton beam, and then attached to the nozzle, there are like two imaging panel. We can acquire the combing CT. That's how we verify the treatment position. A lot of time during the treatment, one treatment like for the prostate cancer, that can be it ranging from 2 fraction to 35 fraction. So with the multiple treatment, patient in between may lose their weight, so we can see the change of the body shape, or the tumor can shrink or grow during the treatment. That's why we want to be able to have a flexible and a fast way to regenerate a plan when we see there are large discrepancy happen between the initial treatment plan and the patient on the couch, the treatment date imaging. So the idea we try to introduce in this framework is we combine the concept of digital twin. recently, we can see there are more and more publications on the journal to show that how the digital twin may impact the healthcare. We see one paper in 2024 from the Nature Digital Medicine. The author defined that digital twin as the virtual representative of the person, which allow dynamic simulation of potential treatment strategy, meaning that this can serve as a digital replicant of the patient, and then we do many different simulations until we find the optimal personalized treatment plan. Another paper published in 2025 on the Lancet Digital Health, they further decomposed the medical digital twin into 5 components that including the patient, data connection, patient in silico, and interface and the twin synchronization. Later, interview paper in 2025 also defined that the multi-model integration become an essential component to turning the static imaging snapshot into the live model of the real patient. So here's the framework we try to propose, apply the technique into the radiotherapy. It can be decomposed in the upper part and the lower part. The upper part will be done offline because the digital twin idea is like we want to leverage the computing power to simulate many different potential that can happen on the treatment day. So what we do offline is we take the population database and then we will perform the deformable imaging registration to bring all this population database into our target patient coordinate frame. And then we try to compare their treatment plan imaging and their combing CT imaging acquired during the treatment, how they vary during the, how the anatomy vary during the treatment. Our fundamental assumption is that the anatomy change, it should be continuous. It cannot have a sudden huge change. So after we're doing that, we can generate multiple predict CT imaging. For each predict CT imaging, we use that to generate the radiotherapy plan. And the lower workflow is like when we, on the real treatment, we bring the patient on the couch and we acquire the CBCT scan, and then we compare the dosimetry parameter, see how it deviates from the original plan. If within the acceptable region, then we can proceed the treatment. If large discrepancy happen, then we can stop the treatment and then initialize our adaptive workflow based on our pre-computed treatment plan database, find out what the optimal plan is, and then use that as the one-star re-optimization prior to achieve the fast plan generation. Here is our dosimetry parameters. Those parameters are taken from the TooSmart clinical trial, meaning that they're targeting the prostate patient and deliver 2 fractions to the patient. The right-hand side figure shows like how do we score the plan, because we will generate like hundreds of the pre-treatment plan. Those plans need to be properly ranked by the computer instead of human. So those parameters will help us based on how good the radiation cover the target and how good the treatment plan spare the normal tissue. Combined with them, we got the composite score. And we compare the imaging of our generated imaging and the original CT scan acquired imaging to the combing CT imaging acquired at the treatment day. We can find out in the following table show that our composite score is like higher than the clinical plan, meaning that we do able to capture some anatomy prediction during the treatment. This bar chart shows the different plan scores. The higher scores meaning the better plan quality we achieve. So we can see that the dark blue line is our proposed method, and the green bar shows the
conventional clinical method, overall, we can generate a better clinical quality. And below, we show 2 examples of how the dosimetry parameter difference comparing to the clinical plan and our plan. And the last column shows the plan quality score and then re-optimization time. So what we're trying to present is that no matter clinical plan or our proposed plan, they can both achieve a good quality score. However, they will require a different amount of time. Given the patient on the couch, we want to minimize this plan generation time such that we can consider that the patient comfort and also our economic of the treatment. This figure diagram shows how the radiation distribution within the patient anatomy. This shows the prostate treatment. And then the lower those follow histogram curve showing that all the plan can achieve the same quality but require different amount of time. If we want to achieve the clinical acceptance quality, our plan can achieve that within the minimum time. And this diagram compared the first row shows the initial plan, like the clinical plan and our proposed digital twin-based plan can both achieve good quality. And the middle row showing that the evaluation imaging at the treatment acquired combing CT, we can see that there are some like under coverage for the target, and then after the re-optimization, all the method can work. So we conclude that this is like a proof of concept study showing that the potential of applying digital twin to the radiotherapy. And yeah, thank you. So last thing, take-home message is like for the future, we are expecting to see more and more application of the digital twin in the medical imaging and use that to support real radiotherapy. Thank you very much.
So study is open for questions. No question. I can start with the first one. So you have some speed up. How much of this speed is coming from anatomical modeling and the other parts? So a better anatomical modeling, what percentage of this speed up coming from?
Yeah, thank you. So we have a speed up about 3 times faster than the conventional clinical workflow. And then regarding for the anatomical imaging generation, because those are generated offline, it will depend on how many GPU available to the server. But the most important things for those offline generated imaging, they are not impact the real treatment. Because from the patient coming into the hospital, acquire the treatment plan CT scene to the first fraction, usually we have like 10 working days, like between 5 to 10 working days. So those offline work can be done like before the initial treatment. What we really worry about is like when patient really on the table, how many time do we need? So for that is the time we report in the table. On the average, our proposed method can be done like on the average about 7 minutes, which is below 10 minutes, while the conventional method require at least like 20 minutes to achieve the work. Thank you.
So I have another question. Yeah. Usually these prostate patients, if elderly, they may have hip prostatitis and they may have unusually large prostate, gallbladder, right?
Yeah.
So for those cases, if this is a digital twin, do you have some detection mechanism for detecting such out of distribution cases?
Yeah. Thank you. That's a great question. Yes, like you mentioned, the hip prosthesis is very important to the proton therapy as it's very sensitive to the proton range. So
one part of in our framework is like the step to generate the corrected CBCT imaging. In there, we will apply our previously developed unsupervised metal artifact reduction algorithm. It will correct the artifact contamination region and then assign the proper material to the heat processes. Thank you.
I think we have time. One more question. I can also ask. There is nobody. So your digital twin is an anatomical model, right? So biology is not there yet. So you just look at the, I mean, I don't want to say just, the geometry is there.
Yeah.
But there is a PSMA PET, radiogenomics, and so many other radiogenomics that you can include some biological parameters into the system as well, right? So that will be your dose calculation and all other things. So is your system ready for accepting such biological parameters to be used, for example, in clinical trial, right?
Yeah, thank you. That's a great question. So far, we demonstrate the feasibility of the anatomical imaging. And like you mentioned, biological information is more informative. It's directly related to the patient outcome. So for those functional imaging is our next step, which is ongoing. So I would like to thank, I have currently one PhD student working on this direction, Yizhou Wu. So that is exactly we are currently working on. Yes, thank you for the suggestion.
If there is no other question, let's thank the speaker again.
Thank you.
Next, we will move on to the spotlight. So the first paper is titled AADAPT, Adaptive Intracranial Artery Segmentation with Morphology-Guided Prompts and Difficulty-Aware Learning.
Hi everyone, we'd like to introduce our work, Adaptive Intracranial Artery Segmentation with Morphology-Guided Prompts and Difficulty-Aware Learning. Let's start with some background. We'd like to answer the question why intracranial artery segmentation matters. Cerebrovascular diseases, including stroke and aneurysm, require reliable characterization of cerebrovascular structures for disease assessment and treatment planning. Clinical evaluation often depends on the analysis of vessel continuity, stenosis, and so on. However, intracranial arteries are thin, tortuous, and anatomically complex, making accurate vascular characterization challenging. Therefore, precise intracranial artery segmentation plays an important role in automated cerebrovascular analysis and quantitative vascular assessment. Now, the clinical reality is that we have not one but several imaging modalities for intracranial vasculature. The two most common are CT and MRI. Quantification, regardless of modality. Putting this together, the problem we need to solve has three technical challenges: geometry, topology, and cross-modality robustness. Let's unpack those challenges. We use MedSam as our backbone, which gives us cross-modality robustness essentially for free. And we also want to give some vessel priors to the model. It does this through inductive bias injection at three architectural levels. One is representation level, telling the encoder how vessels look. And the second one is prompting level, telling the encoder where vessels are, without a human in the loop. And the last one, but not least, optimization level, telling training where errors hurt most. Errors concentrate at thin branches, low contrast regions, and vessel boundaries. The quantitative evaluation shows that our method almost achieves better performance compared with other methods. Shows that some common runs patterns are observed across all results from the compared methods. This includes missed distal branches and discontinuities in thin or low contrast arteries, as well as false positive representation in bone, soft tissue edges, or background artifacts. Here are some limitations and our next plan. We believe that extending this to 3D will further enhance its performance and strengthen its clinical relevance. Thanks for listening.
So our second spotlight is EndoSemis towards robust semi-supervised image segmentation for endoscopic video by Hao Li.
Hello everyone, I'm Hao Li from Vanderbilt University. Today I'll present our work, EndoSemis, a semi-supervised segmentation framework for endoscopic video. Our goal is to reduce the need for the dense manual annotation while maintaining robust segmentation performance in the challenging endoscopic scenes. We focus on the kidney stone segmentation. This task is challenging because frames are not clean images. The stone boundaries can be affected by irrigation, bleeding, motion blur, and debris. At the same time, manual label is expensive and time-consuming for long surgical videos. This makes the semi-supervised learning attractive because we can use many unlabeled frames together with a small label set. However, naive pseudo-label may contain mistake. Here is an example. If the pseudo-label contains a large region of the false negative, which is marked by green, the model may reinforce its own mistakes during training. To address this, we propose EndoSemis for superior pseudo-label. This slide shows the kidney stone segmentation results with only 10% label data. Our EndoSemis achieved the highest dice for this task. This outperformed the supervised UNet and the strong semi-supervised baselines, including CPS, Unimatch, and cross-stitching. The qualitative result shows the same trend. Here is an example where the red is true positive, green denotes the false negative, blue is the false positive. Yellow circle highlights the Turkey regions. Compared to the baseline method, the EndoSemis reduce both false positive and false negatives in these difficult frames. In these slides, we also evaluate whether the proposed EndoSemis generalize beyond the kidney stone. This slide shows the results for cross-center polyp screening experiments. EndoSemis achieves highest dice score, with UNet dice increases from 64 to 71. If we switch to a stronger backbone for polyp segmentation, DSHNet, EndoSemis further reaches 73 dice. We found that the EndoSemis is model agnostic. It improves the dice across different backbones. This slide shows the method is not only limited to one autonomy, one dataset, or one backbone. We have more results in our poster. Please check our poster. Thank you. For the code of our work, please scan this QR code.
Next, we have helioscedastic heat map regression for reliable pectoral muscle segmentation in mammography.
Hello all. My name is Paul Zech, and I'm going to present to you our work about modeling uncertainty in pectoral muscle segmentation. The pectoral muscle is a key anatomical landmark in mammography, and its segmentation is an essential preprocessing step. Due to its positioning in the upper corner, segmentation can be achieved by finding the contour that delineates the pectoral muscle from the breast tissue. However, finding this contour can be highly challenging, even for physicians. In some cases, for instance, dense breast tissue can occlude the muscle boundary and the exact position of the contour is uncertain. This ambiguity is an inherent property of the input data itself. Therefore, we explicitly uncertainty to identify unreliable segmentation results. And here's how we approach this. First, we pass the mammograms through a standard unit to produce a spatial heat map. The key step here is we apply a row-wise softmax operation, and this turns each row of the heat map into a full probability distribution over possible contour positions. From each row's distribution, we can then extract the mean as our contour prediction and the standard deviation as our uncertainty measure. We can then train this end-to-end with a heteroscedastic loss function, which conditions the uncertainty on the input images. Additionally, we add a shape regularizer that encourages the model to produce well-shaped distributions. So how can we systematically evaluate the model's response to increased uncertainty in the input? We do this by gradually adding more and more X-ray typical noise to the input images and monitor the model's predictions. And what we can immediately see is that as image quality gets worse, the model gradually responds with increased uncertainty coming from the input. Importantly, we can also see that the uncertainty starts from the difficult lower part of the muscle where the occlusion of the breast tissue begins. This means our method is not only capable of capturing uncertainty that arises from the input, but it can also localize it. But one important question remains. Why do we model uncertainty with heat maps and full probability distributions? And what do they reveal about why the input is uncertain? I'll be very happy to discuss this further with you at the poster session right after the spotlight talks. See you there.
So our last presentation of our session is by Nina Wang. Sec4Sec is a segmentation systematic failure models study by using subgroup discovery methods.
Hello everyone, my name is Nina and I will present our work Sec4Sec identifying systematic failure modes in segmentation by subgroup discovery methods. This work is selected as a spotlight presentation at MIDL 2026. Subgroup discovery methods are really useful for understanding when and why a model fails. For example, earlier work found that one key difference between the best and worst performing groups was whether a chest strain was present in the X-ray. This reveals that model was using chest strains as a shortcut for predicting pneumothorax. By balancing the prevalence of chest strains across gender groups, researchers were able to reduce the performance gap, a problem that had been difficult to solve for a long time. But most subgroup discovery methods have only been studied for classification tasks in medical imaging. Segmentation is still largely missing. And beyond that, there's no clear way to evaluate subgroup discovery results, or even a good taxonomy of different types of systematic failures that can happen in segmentation. So in this work, we first defined a taxonomy of segmentation failure modes based on previous literatures. Those are shortcuts, label noise, underrepresentation, and difficult cases. We designed experiments accordingly, used both artificially introduced errors and the original dataset while keeping the setup as close as possible to real-world scenarios. The overall framework for subgroup discovery contains 3 parts: information embedding, sample clustering, and inspection. Due to the difference between the segmentation and classification task, we also have 2 add-ons to the pipeline. First, we explore embedding variants that makes more sense for segmentation tasks. And second, we defined clear criteria for what counts as successful subgroup discovery. In other words, when a method has truly found a meaningful problematic slice. Due to the time limitations, we only show one example results from the original dataset. Here we can see that clusters with lower performance tend to contain more low-quality images. The visualization also shows that the samples within each subgroups are systematically similar. Please check out our paper for more details, and if you'd like to try the framework in your own work, please feel free to reach out. Thank you.
So this concludes our session. Thank you very much for attending. Let's thank again all our speakers.
So I'm just going to do a very brief intro. Some of you might be wondering what Melba is, and hopefully many of you know about Melba, but just it's a journal that we started. At this point, it's a little over 5 years ago, I think, and it's machine learning for biomedical imaging. We still believe that journals have a special place in science, despite the fact that the field is moving very fast, and conferences obviously is a good way to disseminate your work. We still think that there's a place for journals where you get thorough feedback from reviewers, you iterate on your work, and you can present really detailed, deep work in a journal setting. We started this journal really in response to what's going on in the publication world around for-profit journals and how it was becoming very outrageously expensive to publish in some of these journals. So it's a totally independent, community-driven journal that really depends heavily on everyone volunteering their time, including ourselves, right? And we're really devoted to free and unrestricted access. So everything that's published in the journal is free for everyone, and the copyright is owned by the authors themselves, so they can do whatever they want with the material that they're publishing. And we try to really pay a lot of attention to making sure that what we publish is of high quality. So we really work very hard on the reviews of these papers. The scope of this is the intersection of machine learning and biomedical imaging. So the reason I'm up here is I'm the editor-in-chief of this journal. And we have a special relationship with MIDL, which started a couple of years ago. And we've sort of got two sort of special tracks in Melba that relates to MIDL. One is the conference to journal track. So every year, MIDL has a special issue now in Melba. So a bunch of the papers that are invited for this get sort of to publish their extended versions of their articles in Melba. And the other is the journal to conference track, where basically any original research article that's published in Melba, not a special issue article, but an original research article, is invited to be presented at that year's MIDL, right? So and this is the current session that we're going to be at, are basically papers in this category. And I'm a really big fan of this track because when you're submitting your work to a journal, you always have the FOMO of like you're missing out on like going to a specific conference and presenting your work and meeting people. And I think this sort of brings together the best of two worlds. And the last thing I want to mention is we have a new resource track that we introduced this year, basically dedicated to publishing data sets and benchmarking. And this was spearheaded by Spiros, who's not here at MIDL, but who's really a sort of a leading figure in benchmarking in this community. And so we publish two types of papers here. We publish open data sets and we publish software products. And we have like a whole sort of way of evaluating and organizing these papers. There's templates that we have that we share on our website. So I'll hand this over to Ipek and OL, who are going to chair the session. But we really are, depend on you guys. So and we think of ourselves as hopefully approachable. So feel free to email us or reach out to us if you have any thoughts or ideas about how to make Melba a better journal for the community. Thank you.
Thank you to Mart, who is so eager he didn't let us introduce him. So thank you for introducing us instead. I'm Ipek Oos.
I'm still OL, I'm still at the University of Amsterdam, but in this context, I'm also the full disclosure publication editor of the Melba Journal. So without further ado, we'll have our first talk entitled Radar, Rapid Anatomy Independent and Deep Learning PDFF, and that's a very long title that I'm sure the author is actually very eager to explain to us now. So the floor is yours.
Test. Okay. Okay, I'll restart. Thank you for the introduction. I am grateful to be here to present the paper on behalf of the first author, Dr. Timothy Bray. So today I'd like to talk about our work Radar that tries to estimate PDFF NR2 star. So let me first start by explaining what these are. So firstly, PDFF stands for proton density fat fraction, and it's a way to measure fat content in a voxel where we assume that it is composed of two types of tissue, one being like fat and the other one being water. And PDFF can be calculated as the ratio of the proton density coming from fat to the overall proton density. And PDFF has found applications across many organs and diseases, with applications in obesity and cancer, for example. And R2 star is a relaxation rate that decays the signal in time, which is a confounder of PDFF, and which means it's important to estimate to reduce the bias in our PDFF estimates, but it has found use as well in applications such as iron overload. So how can we determine PDFF and R2 star? What we would like is maps that look like this, of the tissue properties across the volume, but we first need to acquire multiple measurements with different settings, in this case echo time. And if we were to look at a single voxel in the volume, we can define a tissue property vector Y composed of PDFF and R2 star for this voxel, and do the same for our signal vector. And in conventional fitting strategies, we start by making an initial guess for the tissue properties, and using a biophysical model, we can make a prediction of the signal for that tissue property. And using some gradient-based optimization strategy, we can fit the model to the data. And in general, we want to make the predicted signal as close as possible to the measured signal, which you can do by maximizing a likelihood function between them. And then we update our tissue property, and we repeat this over and over until we get what we deem to be a good estimate. The problem is that this strategy is iterative, and it must be repeated for each single voxel in a volume, which therefore means that this carries a substantial computational cost. So what we would like to have instead is a method that can rapidly estimate PDFF and R2 star. And for this, deep learning-based approaches have been proposed. But so why can deep learning be faster? Well, it's that if we have learned a function to do this, then we can just get tissue properties in a single forward pass, and we can avoid the iterative process of this. And in order to learn this function, that directly maps from a measured signal S to tissue properties Y. In a supervised learning paradigm, we base ourselves on a set of known mappings that we have where we pair a signal and the tissue properties that produced it. The natural approach to learn this mapping is to use a voxel-wise strategy, which has been a standard in diffusion MRI applications. And this has been the topic of work of a substantial amount of work in our institute. And the advantage of this approach is that, like the conventional fitting, it would be anatomy independent, since it does not rely on any spatial information. However, it's surprising that when we look at deep learning approaches that have been used for PDFF and R2 star estimation, these have tried instead to learn an image-wise mapping, since they've been relying on CNN-like architectures. And the problem with these is that relying on spatial information means you are anatomy dependent, and you thus need very large and expensive data sets to train your models, which means it's very difficult to generalize across anatomy and also across pathology if it's not or extremely underrepresented in the training data. So we attempted to perform voxel-wise PDFF and R2 star estimation in simulation, where we know, where we have the ground truth tissue property values. And here I'm showing you a PDFF error map for where vertically you see ground truth values of PDFF ranging from 0 to 1, and horizontally R2 star values from 0 to 100 seconds minus 1. And if we look at this error map, we can see that the performance is quite poor, especially for high R2 star values. For example, in the area highlighted here, we see a very large negative bias for high PDFF, and on the opposite range, we see a very large positive bias for low PDFF values. So the question is, what is causing this bias? Work in our group has previously highlighted this problem in quantitative MRI applications, and the issue is what we call model degeneracy, which is a phenomenon where multiple tissue properties can produce similar signals. And to give you an understanding of what happens, if we take an illustrative voxel here, and we look at the likelihood function for different PDFF values, there are actually two maxima. And in a conventional fitting problem, when we're trying to do conventional fitting, this is a problem because we can end up in estimating tissue properties that correspond to either maxima, depending on how we initialize the algorithm. But how does it affect machine learning? Well, if we come to the previous slide I was showing you, and we instead look at the degenerate case, so here it's an extreme case where a single signal, so two different tissue properties can produce exactly the same signal, means that our degenerate signal maps to two different tissue properties. This is a one-to-many mapping, which is not a functional relationship, and our neural network that we're trying to train is itself a function and therefore cannot represent this type of mapping. And what ends up happening is, if we're trying to minimize the mean squared error, is that the network learns to map the empirical mean of these tissue properties. Of course, meaning that we thus see bias in our parameter estimates. And to give you an illustration of what happens in the voxel-wise case I was showing you before, we now see that for different noise instantiations, our estimates, instead of being at either of the maxima, they're scattered in between the two. So the solution to this problem is about appropriately designing our training data distribution, which was also highlighted in the paper I was discussing with you before. And the solution relies on something that was invented by Christopher Bishop, famous author of the PRML book, in 1992, where in their setting, only one mapping was physically plausible. So what their solution that they proposed was that if you could divide the parameter space and eliminate the region with the unphysical parameters, well, you can then restore one-to-one mappings in your training data. The issue is that for PDFF, both our solutions are physically plausible, so we can't just naively eliminate one of these. So what we propose instead, which is the novelty of Radar, is the use of a dual neural network approach. So how can we apply this training data distribution design concept to our problem? Is that if we go back to the previous likelihood function I was showing you before, if there is a switching point close to PDFF equals 60% that enables to separate where each of these two maxima lie in parameter space. So below PDFF close to 60%, we see low PDFF solutions, meaning that we can train a network that hopefully restores one-to-one mapping on this area of parameter space. And similarly, we could do it on the other side for PDFF superior to 60% with our high PDFF solutions lying in this area of parameter space. So when we do this, we actually see that one-to-one mappings can be restored. So both low PDFF and high PDFF networks see very low bias in the areas of parameter space that they're trained on. And however, as expected, we see large bias on the region of parameter space that the network was not trained on. But since we need good performance at both low and high PDFF, we can't just use either of these networks. What we instead propose is to feed the measured signal to both low and high PDFF networks to get two different candidate solutions. And if we compare them based on likelihood, we can then select the one that maximizes the likelihood as our final parameter estimate. And this is analogous to multi-start strategies that have been previously proposed in conventional fitting. So now that I explained how radar works, let me quickly show you how it performs. So in silico, where ground truth tissue properties are known, we see very similar performance to conventional fitting. However, the main advantage is that the processing time is of 3 orders of magnitude faster. So we go from something like 27 minutes to 3.7 seconds to get tissue property estimates. And if we were to look at our in vivo results, unfortunately, we do not have access to ground truth data, but we can compare our maps to those of conventional fitting. And we see that there's very minor differences across, in this image, for example, of the thorax and abdomen, but we also across different anatomies, for example, here in the pelvis and thighs, as well as this slice of the pelvis. So to conclude, we propose radar, a method for PDFF and R2-star estimation that is rapid thanks to the use of deep learning, anatomy independent due to its voxel-wise nature, and can mitigate degeneracy via the use of neural networks and the use of concepts in training data distribution design. One limitation of supervised methods is that they can suffer due to distributional shift. And for this, self-supervised learning has been proposed in the context of quantitative MRI. And if you're interested in seeing how one can potentially mitigate degeneracy in such a scenario, this is work that I've previously presented at IDMI 2025 that looks into this matter. Thank you very much.
All right, thank you very much for the nice presentation. We have a few minutes for questions, if we have any from the audience. Well, I will start with one, and I think you hinted at it near the end. I was going to ask how, and if you've tested how your method is resilient to extreme outliers, either extremely low levels of body fat or the opposite. Is this basically a domain shift almost that has a negative impact on your results?
If domain shift has...
Well, not purely domain shift, but let's say you take...
Because it's two different things, right? The zero, like you were talking about pure fat or pure water.
Let's say you take bodybuilder ready for competition, 4% body fats.
Okay.
Will you completely mess up the estimation?
Yeah. So in simulation, we were looking at the whole range of physically plausible parameter values for fat fraction, going from 0, which represents, well, only water, or 100%, meaning pure fat. So in simulation, at least, we see the performance we would expect in these types of situations. Regarding what you were mentioning about a specific bodybuilder or something like that, we haven't looked at large clinical cohorts yet in this type of, this is not something we have to still look into.
Thank you.
Yeah. Thank you for a nice talk. You did everything on single voxels, so for every voxel you evaluated there. And I was wondering if taking the neighborhood into account might help you in essentially entangling this distribution and maybe finding solutions that are consistent with neighboring voxels to essentially help you picking the one maxima over the other one in the probability distribution.
To look at the neighboring voxels.
Yeah.
Is that what you're...
Yeah. Is this something that's done, or is this...
This is not something that we have done here, but something you could definitely do. Then you could run into potential issues at boundaries between tissues when trying to then determine fat fraction. But yes, this is definitely something that you could look into, yes.
Okay, thank you.
Do you have a question? Or? Quick question.
Thanks for your sharing. So I guess I didn't follow the 1-2 many. Your figure show your 1-2 many.
Which one? Sorry.
You show a figure.
Yeah.
Yeah. 1-2 many. I think the many is different components. Means fight and water.
Well, sorry, I'm not sure which.
Yeah.
This one.
Yeah, so this Y and Y1 and Y2 is different components.
Yeah, so this Y1 and Y2 is this is just an illustration, but it's trying to represent Y1 would be this would be for one specific voxel.
Okay.
Like for one specific, the Y1 would be the the low PDFF tissue property.
Yeah.
And
okay.
Y2 would be the high PDFF tissue property.
Yeah.
But yes.
Yeah, I got you. Yeah, the S is a measurement signal. S is input.
Yes.
Yes, a measurement signal.
Yeah.
So, but I think for the PDFF.
Yeah.
How many echo you?
We've used 6 in this. 6? Yeah.
So you have 6 echoes. You have 6 measurements.
Yeah.
So finally, the model will output the 2 components. Generally, output the 2 components, water or fight, right? So you mean the 1-2 many, the S means the measurements. So, but you got the 6 echoes, right?
Yeah.
So the S is means 6 echoes.
Yes.
Okay. Okay. Thank you.
But it's what it's trying to represent is that there's many.
Sorry to interrupt. In the interest of time,
sorry.
If you could continue after. But thank you very much for the presentation and for the questions.
Yes, so our next speaker is Alyssa Herring, who's going to be talking about robust general mass segmentation on CT images, a validation study of an AI-based framework. Thank you.
Perfect. Yeah, thanks for the opportunity to present our malware paper here today. The work was led by my talented PhD candidate, Sarah de Boer, who unfortunately cannot be here, but I guess is now watching online. So hi, Sarah. And the talk is about ReNANet, a model for kidney and renal mass segmentation on CT. And in this talk, I would like to focus how we think this model should be evaluated to have clinical impact. So it very nicely fits to what Mert has told us earlier, so thanks for that. What makes kidney cancer challenging? So first of all, the symptoms are often developed very late. So tumors can become very large before they are detected, as you can see here in this example. And at the same time, imaging alone often does not clearly distinguish between benign and malignant tumors, for example, between RCC and oncocytoma. And we have several treatment options. We can have active surveillance, a partial or radical nephrectomy. And that means segmentation is not just a pre-processing step, but it really can help to make decisions in the treatment. And the work is part of the COMFORT study, an EU study, and where the main goal is to develop AI-based support for clinicians to improve treatment planning and care for patients affected by kidney cancer. And ReNANet is just one component in this pipeline, as you can see here. We have multiple subsequent tasks after that, as well as some scoring, visualization, and eventually clinical decision support. So let's talk a little bit about the model that Sarah has developed, because in the beginning we thought, well, we just take one of the already publicly available models, but there was none that was available to download and properly evaluated. So we thought, well, let's quickly train it. We took some data from the Kids Challenge and also some in-house data that we had and trained the NN unit. Rather simple, straightforward thing to do. And the more important part for us was then to evaluate it properly. And for that, we collected some in-house data, 50 cases from Rapport UMC, with some where we only have healthy patients and some with some patients with renal masses. Additionally, we took some public data from TCGA from the US, and we got a data set from Charité in Berlin for kidney cancer patients of 1,500 patients, which is a very large number to really properly evaluate it. And we picked different metrics for segmentation, DICE, Hausdorff for detection, and we did some subgroup analysis for the robustness and compared it with two different other models, the total segmentator and the BUMP model. So let's go on for the results, and first the healthy kidneys. So what we see is that for the healthy kidneys, the renal net and the total segmentator perform very similar, which is great because we know that the total segmentator was very well evaluated for healthy patients and works well for that. But for patients with renal masses, we already see a slightly different picture. And there we see that the total segmentator does not work well for all types of patients. So for some, it works still rather well, but others not anymore. And that is because of the very huge tumors that sometimes take over the kidney that you cannot understand or see the shape anymore. And then that model is failing. So it shows us that we need a dedicated model. And in the next step, we looked into the renal masses and have seen that here the total segmentator fails completely. So it does not even detect any lesions, even though they have that class. And the renal net performs with a better or achieves a higher DICE score than also the BUMP model. And that were very great first results and showed us that we can use it, and we wanted to look into more details for the different classes. So we looked in our Charité data set into the differences for the sex and also the different age groups. And what we see here is that it performs rather similar for all different subgroups, which is also a good sign for us that we can use this model in our pipeline. And then we looked into CT contrast phases and subtypes. And for the contrast phases, at least as long as we have contrast, our model works well. When we do not have contrast, also there we see a failure mode because it was not trained on it. For the different subtypes, we see some differences, but that could also still be explained by the lower number of, for example, oncocytoma in the test set, such that we then have a higher variability. And that is already the first part of the paper, and we put that online on archive and were then contacted by a radiologist from Denmark saying, hey, that's a great model you have. I have now a cohort. Does it also work on that? And the cohort is about patients with, that are in active surveillance, meaning they are very small lesions and you just follow them up over time. And at the moment, they still use routine dose CTs for that. But the question is, couldn't we also use low dose, and would then the model still work? And we tried that by a simulated study to reduce the dose for those scans, and also in a subsequent step use a deep learning-based denoising to also reduce the noise, and then applied our model and compared the different variants against each other. And what we find is that even for a moderate dose level, the model was robust with and without the denoising. And that the volumetric measurements are robust, more robust than the diametric measurements that we did, which is also an interesting finding. And the AI-derived tumor diameters on moderate dose levels are in agreement with what radiologists would also draw on those scans. But very small masses are sometimes missed, because that was not what our model was trained for. When they're really small, then yeah, that can still happen. So it would be good to enrich the training data set to also compensate for that, and then also for this task it could be used. But now we want to go one step further and evaluate it also in this in a prospective study, where the goal is to evaluate the full pipeline that I have introduced in a way that the CT scan is given to our AI platform, and segmentation models and scoring models are run. And then we have two variants, one for the radiologist and one for urologist, who can then use the AI output for reading. And it's just the same image as I have shown before already. That is then the whole pipeline. So we have the kidney and kidney abnormality segmentation, but also vessel segmentation. After that, we differentiate between cystic and solid, Bosniak, subtype classification. So a lot of different models that depend on each other, but it's important to see our model not as just one model, but a component of the whole pipeline. What is the impact then on also the other parts of it? So we designed together with Quantip an AI node for this, where we have a customized interface for radiologists, but also the urologist. And the workflow is that the radiologist review and corrects the AI segmentations if needed, or gets the scores and correct it, and then urologist would get this corrected output and can use it for treatment planning. And this is a very nice example why segmentation is so important, also 3D segmentation, and not just from the dice score, but also just the visualization. Because in this example, it should now also run. No? Well, the animation doesn't work, but I think it's also good like this. We see in yellow, that is a cyst. It's bigger than the tumor, but it's important to realize that where both of the cyst and the tumor is located, and how we now could perform a surgery. And that can also be used to talk to the patient, for example, to explain them which treatment options do we have and how to perform them. And especially the closeness to the vessels is important for this. And this is something we want to also consider in our evaluation. So of course we will still look into technical components like lesion detection or classification accuracy. But when we then look back to this here, it's much more important that we find, of course, the tumor and the big cyst, but maybe we missed the smaller one, and that's fine. So also not every false positive or false negative is this, or weights the same way. So that's something that is really important to understand. And that's a question we will ask. How much does it influence your clinical decision when I miss this one lesion? And how does it influence your understanding of the case based on the visualization, based on the metrics that we provide? And how does it change the experience? Because maybe they do not do anything different than without AI, but maybe, and they're also not faster, but maybe they just experience as less mental effort to perform the task, or they are more confident in their assessment, how they do it. And yeah, that are all things we now want to evaluate, and it's also, again, another next step to really understand how to use the segmentation model. So, the take-home message from my side is models should not be only evaluated as algorithms, but as components in a clinical workflow. And if you now also want to work on kidney cancer, we use the renal net to annotate even more data, and that's now the first step, and that then clinicians, radiologists correct it, and we uploaded it for everyone to use together with other clinical metrics, because it was a TCGA data set. So please free to do that. And when you don't know what to work on, I could recommend you to read a paper from Myrte, where she exactly looked into what is the clinical workflow and where do we still have gaps and where could AI help the most. And with that, I would like to thank you, and all the resources are openly available, so please use them.
The floor is open now for questions. I guess maybe while the room warms up, I will ask one. So I thought it was very interesting that you were saying not every missed tumor matters as much, right? Which is against the intuition that I had, that I thought you were going to worry about everyone. And I wondered, is there a way for you to get data on what it is that will matter? Like, can you have your clinicians actually annotate that for saying, this one I really want to know, this one not so much? Or do they not know either, perhaps?
Yeah, so important to differentiate is between tumors, even though they can be benign or also malignant, and cyst. Because when we look into this room, well, we are quite young still, but in the 60s, at least half of the population have cysts, and they can grow quite large as well. So for those, because we always treat them as the same, or often as the same, there it matters less when we, for example, miss a lesion. And, but we will exactly ask that question. So how much would missing this particular lesion affect your treatment decision? And what would you now do different? That's exactly a question. And let's see what we get out and how that, what you can learn from that.
Right, this is very interesting. And I wonder if then, like, perhaps your model can try to predict that as opposed to just having the binary segmentation, right? Very
yeah, it's an interesting and really cool idea. So if we can learn that as well, to say, here we really have to be focused on, here, and here not, and just train a model with that as well. Yeah, that's a cool idea. Thanks.
Any questions from the room? Going once, going twice. All right, let's send the speaker one more time then.
And now for the last talk of the session, we have now denoising diffusion models for anomaly localization in medical images, presented by Julia Walleb.
Okay, thank you. I'm going to present our work on diffusion models and how to adapt them to the task of anomaly localization. And this was a paper that was published in Melba in November. And it is a review paper, so I'm not going to present you anything new. But I am going to give a summary on how we try to categorize different concepts on this topic. So overall, the idea is to take a medical image as input, and we want to train a diffusion model that is able to identify any pathological region in this image. And for this talk, I will follow the same structure as we have in the review paper. So first, I will give a short background. Then we will walk through different supervision schemes. Then I will give an overview of the data sets and code that we collected. And in the end, we will discuss current challenges. So what is anomaly localization? So in general, the question is where in the image an anomaly shows up. And depending on the labels that we have available, this could be a segmentation task, but it could also be a bounding box detection task or a line deformation task. And in this review, we really focus on diffusion models and how to tackle all of these tasks using generative AI. And diffusion models by now are a very well-known class of generative models that depend on the forward noising and the reverse denoising process. And they are really designed to generate synthetic data. So during inference, we can start from random noise and iteratively walk through the denoising process until we end up with a synthetic image that looks real. But in this work, we are not interested in generating synthetic data, but we are interested in how we can leverage the nice properties of diffusion models for the task of anomaly localization. And for this, we need to add some conditioning and guidance to the diffusion models to solve this new task. And when it comes to conditioning and guidance, this really depends on the type of labels that we have available in our data set. And in the review, we covered different scenarios ranging from full supervision to weak supervision to self-supervised and also unsupervised learning. And when we start on the left, in full supervision, we assume that we have pixel level labels available for all lesions that we look for. So if we have these pixel level annotations, we actually have a pairwise data set that consists of the input images as well as the corresponding segmentation mask. And then we can use the generative process of denoising diffusion models to generate the segmentation mask. So here from left to right, we start from random noise, and we want to generate the segmentation mask, but conditioned on the input image. And this conditioning happens through concatenation. So in every step, we can concatenate the input image to the noisy segmentation mask. And so overall, this works well, but it's like a super slow segmentation model. But the nice thing about this setup is that the diffusion model in itself follows a stochastic process. So we can follow this whole pipeline multiple times, and then we can generate an ensemble of segmentation masks. And when we then compute the mean map and the pixel-wise variance map, this highlights regions where the model is not sure about its own prediction. And this is really nice for interpretability and trustworthiness of the models. Then, so we've seen if we have this pairwise data, we can look at full supervision with conditioning through concatenation. However, in all the other scenarios, we don't have such pixel-level labels available, so we need to consider something else. And for all the other cases, we look at reconstruction-based anomaly localization. And reconstruction-based anomaly localization works like this. So here we use the diffusion model for image-to-image translation. So we take an input image that may show a patient, and we use the diffusion model to generate the pseudo-healthy reconstruction. So this is the same patient if they were healthy. And if we do this in a smart way, we can then take the pixel-wise difference map between input and output, and this difference map will highlight any pathological changes. So if we start with weak supervision, here we don't have pixel-level labels anymore, but we have other labels. So for example, we have image-level labels. And in this case, we can train an auxiliary classification model that can distinguish between healthy controls and a set of patients. And once we have trained this classification model, we can walk through our diffusion pipeline. So we take an input image, and first we add L steps of noise to get a noisy image XL. And then we apply the diffusion model for L steps, but now we guide this diffusion model with this auxiliary classifier towards the pseudo-healthy reconstruction. And then, in the end, we again take the difference between input and output to get our anomaly map. In this pipeline, the critical step is really this noise level L. So how much noise do I add to my image? And here on the left, you see the input image. And then from left to right, we add more and more noise. And you see if we don't add enough noise, so the second column, we don't really change much about the input image. So we don't really find all the anomalies. But if we add too much noise on the right, we completely destroy our reconstruction. So the sweet spot is somewhere in the middle, but this really depends from image to image, and it's really hard to tune this across the whole data set. Then the second problem is that with this weak supervision, we really have a bias towards the pathology we are looking for. So in this case, we wanted to remove the tumor, which actually worked quite well. And if we would compute the die-score wouldn't be too bad in this example. However, the ventricle here on the right is still completely deformed and doesn't look healthy at all. And so these models are just biased towards finding the tumor, but they will ignore anything else that they didn't see during training. Then, in the next step, we look at self-supervision. In self-supervision, we have a data set of healthy controls available. And the idea is to simulate anomalies. So from left to right, we generate a set of augmentations that look diseased in some way. And then we use a diffusion model to map back to the corresponding healthy control. And this is nice because we can simulate all labels that we want. However, here the limitation is that we need some prior knowledge on how the anomalies look like that we actually want to find, because otherwise we can't train such a diffusion model to map back. But also, this setup comes with quite some limitations. So this is our figure of failures. And here on the left, you see that the anomaly is right next to the ventricle, and the model fails completely to detect it because it thinks that it's actually part of the ventricle. Then in the second example, we have a tiny lesion, and in these reconstruction-based approaches, it's really tough to find small lesions. And also what happened quite often was that the model actually finds the lesion, like in the third case, but it only partially removes it. So we only have an anomaly map that is actually smaller than the actual anomaly. And the last example is my favorite. So here we have a broken arm. So we have a fracture in 3 spots. And the diffusion model actually does a good job at mending the bone, so it removes the fracture. But when you look at the bone itself, it still has this weird bend that doesn't look healthy at all. So it doesn't manage to straighten the bone in this setup. And then if we continue to unsupervised learning, in unsupervised learning we don't have any labels available anymore, and we train only on healthy data. So we move to representation learning, and a lot of approaches rely on latent diffusion models. And in latent diffusion models, we first train an encoder-decoder architecture, and then in the latent space we train the diffusion model, which is nice because then the diffusion model is computationally cheaper. And once we have trained all of this, we move to inference, and during inference we may feed an image of a patient through this encoder-decoder architecture, and in the latent space we apply the diffusion model, and because both models only saw healthy controls during training, the output will be our pseudo-healthy reconstruction. And here the problem is that on one hand it's nice because the diffusion model is cheaper. However, the problem that we encountered is that the actual computational bottleneck is now in the encoder-decoder architecture. So it's really hard to find a good 3D autoencoder that works well for anomaly localization. Another problem is that since we rely on this training data set of healthy controls, this data set should ideally cover all healthy variations, which is basically impossible to achieve. And also, what we struggled with is when our test data set then suddenly comes from a different scanner, from a different hospital, this data set shift between the training data set and the test data set in itself will be discovered as an anomaly, and this is not what we want. So in general, we saw that depending on what labels we have available, we can choose different supervision schemes and adapt and condition our diffusion models accordingly. And in the review, we collected data sets that are publicly available, and we also provide links to all of these data sets, and we classified them by modality, anomaly type, and also annotation type. And also, we collected a list of GitHub repositories where all of these methods are implemented and that are also publicly available. As for the current challenges, given all of this prior work, one of the big things is really the computational costs when we move to 3D. So nowadays, there's a lot of work that goes into memory-efficient diffusion models for 3D and also models that speed up the sampling times. However, all of these newer and fancier methods still need to be adapted to the task of anomaly detection. Then the second one is this detection bias that I already mentioned. So if I ask you where in this image the tumor is, I think all of you could give a pretty accurate answer. But this is actually not the hard case. So sometimes you have really rare or small and subtle pathologies or deformations, and these are really hard to catch. And in our benchmark data sets, they are also very underrepresented. So there is a need for benchmark data sets that cover a bigger variation of all our anomalies. And also the evaluation metrics we have at the moment, they are unfair and they are biased towards these large, obvious anomalies as well. And then at the end of the day, of course, we will need to get regulatory clearance. And at the moment, there are some studies that go into prospective studies with clinical endpoints as opposed to computer vision metrics. But also, we will need to have models that are robust across scanners and that are also able to catch like the small lesions and deformations. And now there is also a lot of work going into uncertainty estimation and case-level rationale using large language models. So overall, we've seen that depending on what labels we have available, we can adapt diffusion models such that we can use them for anomaly localization, and we get these anomaly maps. However, the research gaps that we identified in the review were, on one hand, so the computational issues of speed and memory requirements. And then from the validation side, we need better benchmark data sets and also metrics that are fair across all different types of anomalies. And for the clinical validation, we will need to check whether they actually bring a benefit into the clinics or not. I thank all my co-authors, especially Cosmin, who was the first author on this paper, and I'm happy to take questions.
All right. Well, we have a very eager question, so.
Hi, a very nice overview. Thank you very much. So you mentioned that you need access to healthy data for quite a few of these models. Can you comment a little bit on how it's feasible for CT? For MRI, this is maybe easier to get, or even for ultrasound, but for CT, that's not normally done on healthy people, right?
Yes, so a lot of these methods actually, yeah, they need, no, except for the fully supervised approach there, we don't need healthy data. All the others, they need healthy data for this image-to-image translation, and this is actually a problem. So what we did a lot, which is not really a solution, but we took 3D volumes and tried to divide them into slices that are healthy and keep the others that are unhealthy as the diseased cohort. But this is also hard to, like, you introduce a lot of bias there into what slices you select, and also you need to be careful about not to leak any data from one data set to the other. Yeah, this is definitely a gap in evaluation for training, yeah.
Okay, thank you.
Okay, and I think we have time for one quick question with a quick answer. Okay, we have.
Yeah, thank you, great talk. Following on that question, what's your opinion on using fully synthetic data, for example, for healthy data, generating healthy data? I think there are very good models now, and yeah, what's your opinion on it?
I missed the first part. My opinion on what?
What's your opinion on using synthetic data for the healthy part? Just using synthetic, or maybe some part of it?
I'm not aware of much work doing this. You mean using healthy data to train the anomaly detection model? I think this could be like a workaround on what Matthias just said, that we have healthy data available. Maybe we need to, like this issue here, that the healthy data actually should cover all healthy variations. I think we need to be careful that the synthetic data set actually fulfills this criteria, but I guess then we could try.
All right, so let's thank again the speaker for the presentation and the questions.
This concludes the session. We are next up with Matthias Heinrich, who's going to be talking about the Cobra Challenge. And then we will have the poster session. Thank you.
Hi. Yeah, I'm just going to very briefly say a few words about MIDL challenges. And if you are interested, you can get some more info on the COPA challenge, which will happen this and next year. But yeah, otherwise feel also free to join the poster session already now or just afterwards. So MIDL challenges are a little bit different maybe than you know from other conferences. We don't do them as on-site events during the main conference. but we try to advertise them during the event so that then people can sign up for it, yeah, get involved and start working on the challenge. And then, for example, in this Cobra example, we will have people that got good results on the challenge present at the next MIDL in 2027, wherever that will be. So, yep, if you have some interesting data, clinical problems that you think are relevant for the community, please get in touch with us. The process is not as structured as the one for other conferences you might know. You can just send an email to board@middle.io, and then we can discuss the terms on how you kind of present your challenge proposal, and we can revise it, and hopefully you get a presentation like this. But without further ado, I'll introduce Attila Simko, who's not the main organizer, but he's involved, and he's best qualified to present this Cobra challenge to you.
Thank you very much. So my name is Attila, and I'm here to share some info about the Cobra Challenge, but I'm not that I'm not the main organizer, but I'm not an organizer at all, but I'll try my best to answer if you have any questions. So the Cobra Challenge here aims to reconstruct raw CBCT projections into planning CT quality 3D volumes. As already discussed a few times today, a CBCT is taken at nearly every treatment fraction, but some of the imaging artifacts and other motion artifacts as well are just making it really hard to use the CDVCT directly for quantitative tasks. And the main issue here that there is no real ground truth or no real data with ground truth to it, because the planning CT and the treatment CBCT are acquired at different times, so they must be registered to each other, and we know that the registrations are somewhat imperfect by their nature when it comes to different images at different time points. So what's missing is real ground truth, and that's the whole the problem that this challenge is built around. So just to quick look at some of the artifacts that we have in CBCTs. We have scatter artifacts that corrupt the Hounsfield unit values, and they also kill some of the soft tissue contrast. And to make things worse, there's also noise, which degrades the soft tissue contrast even more. And we also have motion artifacts that mainly coming from breathing for this anatomy, and also it blurs anatomical boundaries. And these building blocks, and perhaps many more, they block reliable segmentation and adaptive radiotherapy for standard Linux, and they also reduce the reliability of registrations. So the task for this challenge is to take the CBCT projections and to reconstruct a 3D CBCT volume, and both of these data types should have the same geometry. And this real data carries the artifacts, and the big data set is split into two parts. So we have the real clinical projections, where you have the authentic artifacts, and it's registered to, deformably registered to a real planning CT. So as I said already, it contains registration errors. And we also have another track of this data set, which is the simulated projections, where you take the planning CT and then you forward project it to sort of simulate CBCTs with their known artifacts. So this one gives you a real ground truth, and it's registration free, but it's also simulated. So both of the data sets have some limitations, but if you put them together, you have the real data, for real ground truth, and with their limitations, but you also have the simulated data for like more rigorous evaluation. Just a quick look at the size of the data set. We have 868 patients. I think the slides are all there in the notes, so let's go with 868. We have it from 6 centers and 2 vendors, both for Elekta and for Varian. And we split this data set into 80% training, 6 for validation, and 14 for the later tests. And coming back to the keynote today, for benchmarking, this makes it the largest multi-institutional, multi-vendor CBCT benchmark. So it also forces all of the methods that, if you take the challenge and you apply a method, it should be by default and by design. It's quite generalizable across hardware and across clinical centers as well. So here a little bit more about the data. we have the two sets of data sets, and they also have their own pipelines. So as I briefly mentioned before, for the real data processing, we acquire the CT and the CBCT, different time points. So we first rigid register them, and then we deformable register them. So we have somewhat reasonable input-output pairs. Then the air pockets in the deformed CT are corrected, and the voxel intensities are also transferred between the CBCTs to the CT. So the CBCT sort of becomes like a synthetic CT, but not really, because it still contains the CBCT geometry. And the synthetic pipeline is a little bit different, because here we only have the deformed CT, which you forward project. You add the 3 artifacts that I mentioned already. So you start with scatter, and then you add noise, and you also add motion artifacts. And you reconstruct the CBCT from these simulated projections. And here we have exact reference as well for the input-output pairs, so it's really good for robust evaluations. A few examples here, first for Electa. You see the 3D volumes as well, both for the original CBCT, the acquired CBCT, also for the simulated CBCT in the middle, and the real CT, and you also see some projections. As you can see, this simulated CBCT follows more the geometry or the anatomy of the real CTs, whereas the CBCT is a little bit more artifact heavy. And then it looks quite different, but generally follows the same trends for the variant data, variant part of the data as well. And being comparable for both of the vendors is one very big part of the challenge as well. So all of the methods that you submit must or should at least generalize very well to both of the vendors. Then the evaluation, we split it into 3 parts. When I say we, I mean they, but I just usually say we. The first part of the evaluation metrics is for intensity. So here you compare the predictions with the planning CT. And you have 2 metrics, the mean absolute error and also the PSNR for Hounsfield unit fidelity. Then you have the geometric similarity, where you compare against the original clinical CBCT. So here we want to make sure that the geometry looks correct. And then we also have sort of higher level metrics that come in perceptual similarity metrics. And it's a pretty good representation for artifact detection. Then we do ranked and mean for giving you the final score, which means that in all of these evaluation groups, you will be ranked, and then the rank will be meaned, and then that will give you the final result. The timeline, the challenge starts soon on the 13th of July. There will also be, if you follow the website, which I will share later, there will also be an online event where you can ask more questions about the data and about the challenge itself. There's fixed compute, so there's a 16 gigabyte GPU that you can use, and for every case you have 20 minutes. Your method has 20 minutes to reconstruct the CBCT. And you can submit up to 3 tasks or methods during validation, and you can only do 2 test runs, and the final one will be your final submission. And I believe you cannot use your own data to further train a model, but you can use already pre-trained models if you want better results. The organization team contains some of the best people I know, so at least do it so that you can get to meet them and talk to them, because they're amazing. And here are a few links to the actual challenge, and also the code and the pre-processing tasks, and also a primary contact number if you want. And thank you very much for your attention.
All right, then thank you again, Attila, for taking over this job, and I wish you all fun at the posters.